universe. Hubble was launched in 1990 by NASA and ESA. It orbits Earth 350 miles, or 569 kilometers above its surface. Due to its position, it can circle free of Earth's atmosphere, which distorts and blocks light from space. Ground-based telescopes are unable to match Hubble's pristine views. Every 97 minutes, the telescope whirls around the Earth collecting light, much more light than our eyes can see alone. From the nature of storms on Jupiter to the distant galaxies of the universe, this light can reveal everything. Hubble sees structure where we see light points. Hubble sees detail where we see the haze. While we see darkness, Hubble sees the faint glow of the early universe. Astronomers have uncovered some of the most fascinating cosmic discoveries of our time thanks to Hubble's explorations and a host of new questions and puzzles that will be explored by future telescopes to push back the darkness. The cosmos. There are many puzzles in a universe. There are times when the things we cannot see are more important than what we can see. We use the visible to piece together the great mysteries of the invisible. Take the behavior of matter around black holes, for example. The mysterious, still unexplained phenomenon of dark energy is revealed by distant stellar explosions. The age of the universe is estimated by studying distant stars. Cosmology is the study of the universe's structure and context. We study how the universe functions as a whole, how it is currently and will be in the future, and how things within it form. Cosmology is a little like being inside a building, examining the switches and outlets we can see on the surface to determine the wiring inside. Space is a vacuum, but its objects are part of a larger structure, and astronomers must understand this structure's physics before understanding how the features function. Looking out at space is like looking back in time. Our location receives light from the farthest objects in the universe that left those objects billions of years ago, so we see them as they were then. How do we see these farthest objects when we capture their light? Most distant galaxies are more minor, irregular, and lack clearly defined shapes. Hubble could see these distant galaxies before any other telescope. After observing a nearly empty patch of sky for 10 days, astronomers turned Hubble on what appeared to be a roughly bare patch of sky. The team was taking a risk. Most Hubble observations take only hours, and the time was better used on less speculative projects. Hubble might not have been able to see the objects the astronomers hoped to find, because they were too faint or too small. The search yielded the now famous Hubble Deep Field image, containing 3,000 galaxies, large and small, amorphous and shaped, burning in the depths of space. Astronaut Hubble looks back in time. The farther Hubble gazes into space, the farther it gazes back in time. Recent surveys, such as Hubble's Ultra Deep Field, HUDF, and the Great Observatory's Origins Deep Survey, GOODS, provide images of vast collections of galaxies, including some that date back to when the universe's time was less than 1 billion years old. The Hubble Space Telescope teamed up with other observatories in the following years to study small patches of the sky in high-resolution, long exposures and multiple wavelengths. This chart shows Hubble's most significant deep sky surveys and their covered regions. We can follow the evolution of the universe with images. The most distant parts of the visible universe are littered with tiny red dots, the shapeless building blocks of galaxies whose light has been stretched by the expanding universe into an infrared glow. As we move closer, we see galaxies colliding and merging, increasing growth. Further away, we see versions of the large, stately galaxies we know today. Seeing how galaxies have evolved can show how the universe we know today evolved from a uniform void to an uneven universe ready for stars and galaxies to form. Furthermore, the differences in these galaxies allow us to learn about the first stages of the universe, the part we can't see. There was already some structure when the galaxies formed, or the spread of matter would have been even. In contrast, we see the coalescing of groups of importance, small pieces that began, collided, and merged. This Cepheid variable star in galaxy M100 doubles in brightness during each pulsation. We are being beamed down from the sky with the answers to the universe's age. We know the universe has been expanding since the Big Bang. So, if we can measure its size and rate of expansion, we can calculate its age. There is more to it than you might think. All estimates are based on the brightness of objects, since you can't extend a ruler to the stars. Cepheid variable stars are a particular type of pulsating star whose brightness cycles indicate their inherent brightness. Observers find Cepheid variable stars in galaxies by comparing their intelligence with how faint they appear due to their tremendous distances, to determine the distance to those galaxies. It's like judging a car's distance from you by judging the brightness of its headlights on a dark street. Cepheid variable stars enable astronomers to measure distances in space. Discover how pulsating stars serve as yardsticks for measuring the universe. Cepheid variables have been found in galaxies as distant as NGC 4603, 108 million light-years away. Their stars appear faint from Earth. It is complicated to distinguish the characteristics of the Cepheids found in NGC 4603. Cepheids were used to determine the distance to the galaxy. Up until Hubble, astronomers could only narrow the universe's age down to 10 to 20 billion years, a measurement with 10 billion years of error. Hubble conducted a comprehensive study of 31 Cepheid variable stars, determining the current expansion rate and narrowing the universe's age down to its most precise point. In combination with measurements by other observatories, observations of Cepheid variable stars in galaxies like NGC 4603 led to the estimate of 13.7 billion years old. With Hubble's observations, the universe's age changed from a vast range of possibilities to a precise number. It isn't just a matter of curiosity to know the universe's age. Having a timescale for the development of stars and galaxies will help refine our models of how the universe and everything in it formed. Numerous elements of cosmology were shaped by the actual age of the universe. Star and galaxy formation timelines required a period. Previous problems with the universe's age range have included things like stars thought to be older than the universe. We can now determine everything from the time needed for stars to die to how long it takes to produce elements such as carbon, nitrogen, and oxygen, the ingredients we need to survive. A watershed epoch is shown on each side. From the Big Bang to the present, it represents the universe's evolution over 13.7 billion years. As a result of reionization, the light from the first stars burned off a fog of cold hydrogen. A later epoch quasar pumped enough ultraviolet light to reionize the primordial helium with the black hole-powered cores of active galaxies. Radio telescopes were first used to study some familiar cosmic objects, including the remains of supernovae, distant galaxies, and influential areas of star formation. The quasars in these images appear to emanate from one galaxy, left, and two galaxies colliding, right. There are 1.5 billion and 1.6 billion light-years between the galaxies respectively. The entity that appeared to be a star appeared to be nothing more than a light point. As quasars are so far away, and their size is so tiny, about the size of our solar system, the fact that we can see them with a telescope makes them among the most luminous objects in the universe. As Hubble proved with its high resolution, there was actually a galaxy hidden behind the glare of the quasar. He contributed to the quasar mystery. The surrounding regions of a supermassive black hole heats up and releases enormous energy and light, creating a quasar. As a result of multiple galactic mergers, Hubble found quasars in the centers of galaxies colliding or brushing up against one another and in elliptical galaxies. Quasars may be lit up by these interactions and fed by the central black hole. Observations by Hubble have also led to the discovery that these brilliant galactic centers are powered by giant black holes. Quasars weren't the only ones involved. According to Hubble, almost all galaxies with bright active centers have supermassive black holes feeding on the galaxy's matter. Additionally, the mass of a black hole is closely related to the mass of the bulge of stars forming the center of the universe, indicating that the formation of a galaxy is closely related to that of its black hole. The study of these monstrous black holes raises many questions about the formation of galaxies and the structure of the universe. Why do some regions form galaxies with massive black holes and others include rather ordinary galaxies? Why does the black hole phenomenon exist over such a wide range of sizes, from giant black holes in galaxies to tiny black holes a few times the size of our Sun? Is the formation of quasars just a stage in constructing supermassive black holes? The universe began with a bang and has been expanding since then, increasing the distance between galaxies with time. For many years, astronomers contemplating the death of the universe considered two main scenarios. Either the universe would keep expanding forever, the galaxies gradually drifting apart, or it would stop growing and collapse in a big crunch. In the late 20th century, astronomers believed the universe would expand forever at a constantly decreasing speed, coasting like a car out of gas, but never totally losing momentum. They began determining the rate of expansion. The brilliant stellar explosions known as supernovae could also be used to determine the distances to galaxies, just as they were for Cepheid variable stars. However, supernovae can measure distances even farther than Cepheids because of their incredible brightness. Astronomers used Hubble's clear vision to find the very distant supernovae needed to calculate the universe's expansion rate. Hubble's observations, however, upended the conventional wisdom. The universe wasn't slowing down. A study of the properties of the supernovae Hubble had imaged revealed that the universe was expanding faster and faster as if it were being propelled. Understanding what is causing this acceleration will take time, since it doesn't seem to be a part of the glowing matter we see. How could this be? Scientists have no idea. A previously unknown dark energy might be the cause, but humans are only just beginning to understand the mysteries of this field. We must develop tests for a phenomenon invisible to us to describe and define dark energy until it is as clear as the stars in our own backyard. For now, Hubble continues to study the supernovae that might hold the key to unraveling this mystery. Dark energy's discovery. Known as Type 1a supernovae, certain exploding stars constantly emit the same amount of light. As a result, their brightness is nearly the same. Type 1a supernovae vary in brightness because some are closer to us and others farther away. By comparing the apparent intelligence of the supernovae with their actual brightness, astronomers can calculate the distances to the supernovae. The distance to the galaxies where the supernovae occurred is also indicated. Astronomers believed the universe's expansion would slow down as the distances to faraway galaxies increased. Cosmologists can measure the universe's expansion rate at different times in the past based on the brightness of Type 1a supernovae. Hubble found that the most distant supernovae were dimmer than they should have been, indicating that they and their galaxies were farther away. This contradicted the hypothesis that the universe expanded constantly or slowed down over time. Only if the universe was growing faster could they make sense of their space. Scientists involved won the 2011 Nobel Prize for Physics for their discovery. The science of the galaxy. Galaxies are islands of activity in a sea of emptiness, where the action takes place in space. We will never be able to travel far enough to see our Milky Way galaxy from the outside, composed of 100 billion to 400 billion stars. While we can observe the activity within our own galaxy and the interactions between galaxies far away, we can also watch the activity within our own galaxy. Hubble helped identify the sources of the universe's most powerful explosions, studied how galaxies formed, and studied stars near the end of their lives. The universe is revealed in its most precise and visible form by our observations of galaxies. Through the study of galaxies, we can observe the dynamics of the cosmos and how things form and change. We observe dominant galaxies feeding off their surroundings and stars, created under the influence of galactic gravitational forces, and puzzle over the varied shapes galaxies take. The study of galaxies past and present is essential to understanding the forces that shape our existence. The minor solar system resides within a universe. The United States Air Force deployed a series of satellites to monitor gamma rays in the 1960s. After signing the Nuclear Test Ban Treaty, the United States wanted to watch for the telltale radiation emitted by nuclear blasts. The satellites immediately began detecting gamma-ray events, but the study ruled out the possibility of bombs. In reality, there was no connection between the bursts and Earth. Scientists further investigated and slowly realized they were witnessing explosions with the power of 10 million billion suns per day, emanating from seemingly random points in the cosmos. Until then, the universe's most violent explosions had gone undetected. Gamma rays. What are they? Gamma ray burst 971214. This galaxy, located 12 billion light-years from Earth, gave off a gamma ray burst in 1998 that was brighter than the entire universe for a few seconds. A release of energy of such a rapid and enormous magnitude had never been seen by astronomers before. The extreme events that produce gamma rays and why we look for them are explained by scientists. The gamma ray burst of 080319b. During a powerful gamma ray burst in 2008, this single object was as bright as 10 million galaxies for nearly 1 minute. The observations followed up on the mystery and concluded that the shots came from supernovae, explosions of massive stars that can produce a black hole or neutron star. Nevertheless, not all supernovae had gamma-ray bursts. What was the actual cause? Observations by Hubble have revealed that many gamma-ray eruptions originate in bright star-forming regions with stars with low metal content. Currently, scientists know there are at least 2 kinds of gamma-ray bursts. There may be a difference between the process of creating a supernova from a star that has lots of metal and one with little. Stars with low metal content are thought to produce black holes when they die, while stars with high metal content form neutron stars instead. Gamma-ray bursts are often black hole birth announcements if that's true. Gamma-ray bursts add another piece to the puzzle of supernovae. Because supernovae are one of the few methods astronomers have for measuring vast distances in space, understanding these titanic explosions is key to understanding the universe. Witnessing the explosion in action can help us determine how it happened. A neutron star is surrounded by gas and dust, all that's left after a supernova explosion. The neutron star N49 emitted a tremendous gamma-ray burst a decade before this observation. Tracing the history of the galaxy. Gravitational pull can cause galaxies to collide and merge. Galaxies crashed more frequently in the early universe than today, and astronomers believe that these collisions are necessary for galaxies to grow and evolve. It is thought that our own Milky Way galaxy, along with Andromeda, has increased in size by absorbing smaller nearby galaxies. We can test this hypothesis by studying the ages, arrangements, compositions, and speeds of stars in a galaxy. The simulation shows an entire galaxy collision sequence and compares the different stages of collision to those observed by Hubble in various galaxy pairs. A combination of simulations and high-resolution observations can help us to better understand these titanic crashes. Observations of 300,000 stars, young and old, in Andromeda's halo by Hubble. During Hubble's time, he observed the halo of the Andromeda Galaxy, a region of stars located beyond the central galactic disk. Andromeda is the nearest large galaxy to our Milky Way, and while it has been observed from the ground frequently, Hubble's resolution allows it to be seen at an individual star level. Because halo stars develop early during galaxy formation, astronomers expected Andromeda's stars to be old. However, they found that the stars in the galaxy's outer regions range from around 13 billion to 6 billion years old. Andromeda would have eaten the smaller galaxies, bringing them into the Andromeda halo and making them their own stars. Based on Hubble's observations, all large galaxies have experienced galaxy mergers and interactions throughout history. Scientists have known for years that the Milky Way and Andromeda are headed toward one another, but it is still an open debate whether they will collide, brush against one another, or miss one another. One day, we'll be able to see that for ourselves. Hubble has revealed that the Milky Way and the Andromeda Galaxy are directly colliding. The two mammoth galaxies will collide in 4 billion years, spinning together in a slow, massive dance, eventually combining into a single universe. The sideways motion of the Andromeda Galaxy was observed by astronomers over 5 to 7 years. Using Hubble observations, scientists predict the future of the Milky Way and Andromeda galaxies. Based on computer simulations, the two galaxies are expected to collide in 4 billion years. Earth and its companion planets will not be affected by the collision, as the Sun is flung into a new region of the galaxy. The distance between stars is so great that there is little chance of stars striking each other when galaxies collide. Stars that are dying. A planetary nebula is a unique and beautiful formation formed by gas heated by radiation from a white dwarf. Over about 30,000 years, mid-sized stars like our Sun eject their outer layers of gas into space, leaving behind their hot core, a white dwarf. Astronomers thought that dim shapes they saw through telescopes were related to planets in the early days of astronomy. We can see previously expelled material interacting with newly ejected material in Hubble's observations, showing that planetary nebulae are not formed in one dying breath, but in multiple outbursts. Many of these nebulae have been observed by Hubble today, and Hubble has observed many complicated and extraordinary shapes, ranging from tunnels to interlocking rings. For example, the Cat's Eye Nebula consists of 11 bubbles of gas that appear from our perspective three-dimensional structure of the Helix Nebula visualization. From our perspective, planetary nebulae seem flat, but they're actually quite complex. There is evidence that the Helix Nebula consists of two nearly perpendicular disks. Although we still do not understand the dynamics that create such intricate structures in such a short time, each Hubble image helps us learn a little more about how Sun-like stars spend their final years. Solar-like stars produce carbon, nitrogen, oxygen, and iron, which are indispensable for life as we know it in their cores. By studying their deaths, we can learn how these elements are spread throughout the universe. A star that is 8 to 25 times more massive than our Sun ends its life in another way by exploding in a tremendous explosion called a supernova, which may leave behind a neutron star or a black hole. Supernovas are the titanic explosions that end a star's life. The star's material is flung into interstellar space at millions of miles per hour during a supernova. The elements formed inside a star are scattered across the area in its lifetime to become part of future nebulae, principles, and planetary systems. Their cores collapse and explode when they exhaust fuel, sending their outer layers racing into space. Astronomers last observed a supernova in our galaxy in the 1600s, when Europe was still settling in North America. In the Large Magellanic Cloud, a supernova, one of the Milky Way's satellite galaxies, reached Earth in 1987. Hubble began monitoring the explosion from the first ringside seat ever for a supernova 3 years later when it was launched. Starburst from supernova 1987A, 1994 to 2006. Supernova 1987A has been observed repeatedly by Hubble, which has seen rings and knots of gas brightening around the exploded star. Material unleashed by the stellar explosion illuminates a 6 trillion-mile ring of gas around the dying star. Over 2 decades of watching the supernova progress have given us a better understanding of how these events unfold over thousands of years. A supernova in the making has also been observed by Hubble. A supermassive star more than 100 times the mass of the Sun, or a pair of supermassive stars, is Eta Carinae. It briefly became the second prominent star in our night sky in 1843. Hubble images revealed that the unstable star had released 2 lobes of hot gas before its eventual explosion. Scientists believe Eta Carinae's mass could lead to a hypernova that would outshine the entire galaxy. The elements denser than iron are produced by massive stars, and when they die, the material is ejected into space. Our solar system was once filled with material from supernovae, as evidenced by your gold ring or titanium watchband. Eta Carinae, the doomed star. Eta Carinae, an unstable star, is expected to explode as a supernova someday. A 150-year-old outburst sent lobes of gas racing outward at 1.5 million miles per hour, 2.4 million kilometers per hour. Science of the planets. The Hubble Space Telescope has observed stars and planetary systems in formation, examined the atmospheres of planets around distant stars, and seen the destructive power of cosmic impacts. What happens on the surfaces of our nearest neighbors? Are there other places with populations that wonder at the skies as we do? As we gather more information about planets and discover new ones, our understanding of planet science expands. Having only 9 worlds on our initial list, including Kuiper Belt object Pluto, is an insignificant sample from which to draw conclusions. The discovery of extrasolar planets, planets beyond our solar system, has stunned astronomers with the wide variety of planetary systems. Giant planets orbiting close to their home stars, planets in strange elongated orbits, even a planet that orbits 2 stars at the same time. Seeing planets within our solar system and beyond enables us to learn more about how these bodies came to be and our own planet. The birth of stars and planets. When clouds of gas and dust collapse, gravity pulls the materials together into a dense object surrounded by a spinning disk of leftover matter. It eventually erupts with jets of intense radiation trillions of miles long, traveling at 500,000 miles per hour, 800,000 kilometers per hour. Scientists are uncertain exactly how the jets form, but believe they result from magnetic fields rotating around the forming star. Astronomers could see jets before Hubble, but not star-forming disks. Hubble's vision enabled them to see both. It captured the first detailed images of jets and disks in the Orion Nebula in 1995. In the past decade, Hubble has taken many images of jets and found the first direct evidence that they originate at the center of the dusty gaseous disk from which the forming star is drawing its raw material. During star formation, the jets are thought to slow down the spinning disk so that more matter can accumulate on the star. The Orion Nebula in a panoramic view. The nebula contains 700 young stars in various stages of formation within a cavern of gas and dust. Astronomers once thought it would be impossible to observe protoplanetary disks, the disk of dust around stars that coalesce into solar systems. The disks were engulfed in giant clouds of gas and dust, making them difficult to discern. By identifying the dark clots of dense dust against the bright background of glowing nebulae, Hubble disproved this theory and found numerous protoplanetary disks. According to Hubble's observations, planet formation is influenced by the environment in which a star develops. The Hubble observations have also provided clues about the missing steps in our understanding of planet formation, such as how a disk of gas and dust evolves into individual planets that orbit newborn stars. Planets outside our solar system. Exoplanet HD 189733b's evaporating atmosphere. Many extrasolar planets have been discovered beyond our solar system. Ground-based telescopes have found most of them by looking for tiny wobbles in a star's motion caused by planets tugging at it, or the slight dimming of light caused by a planet passing in front of its parent star. Hubble can provide insights into the planets that cause these light-blocking periods called transits. In addition, Hubble measures the amount of light passing through the atmosphere of the Earth, which allows it to determine the makeup of the atmosphere. Hubble has discovered atmospheres containing sodium, carbon, and oxygen, and a world with a comet-like tail of hydrogen evaporating into space. In addition, the team detected the first organic molecule on an extrasolar planet. Methane in the atmosphere of a Jupiter-sized planet blisteringly close to its star. Space Telescope's ability to make these observations was a breakthrough, confirming and bolstering the idea that they could examine the atmosphere of far-flung planets and set the stage for current and future telescopes to continue this critical science. Moreover, Hubble took the first visible light picture, something astronomers thought was impossible. Observations of Fomalhaut's dusty surroundings had led astronomers to suspect that the star might have planets since the early 1980s. An image of the dust belt around a star shows a tiny speck of Fomalhaut b, a planet approximately 3 times the size of Jupiter, that might be surrounded by a disk of dust and gas. Observations of the planet Fomalhaut by Hubble. Scientists used coronagraphs to black out nearby light sources, including the star in the center of the image, to observe the much dimmer planet as it passes near a dust ring surrounding the star. Photographs taken years apart show the planet moving along its expected path. For the first time, Hubble observes a planet orbiting another star. Having suspected for years that planets may exist in other solar systems in the universe, the Hubble Space Telescope captures visible light images that provide the first evidence of these extrasolar planets. Scientists describe the discovery of Fomalhaut b, the first extrasolar planet captured on a camera in visible light. Techniques for finding planets. Planets are microscopic compared to other objects in the universe. Moreover, They can be 1 billion times fainter than the stars they orbit. Astronomers have developed innovative methods to hunt planets in other solar systems since they are nearly impossible to see directly. Transit-based hunting. When a planet passes in front of its parent star, it will cause the star to dim slightly as they block some of the light. Astrophysicists watch for these telltale changes in brightness. Radial velocity hunting. The gravitational pull of a planet causes its star to wobble. Telescopes can detect this wobble by observing the starlight broken into a spectrum of colors. As the star wobbles, dark lines appear caused by light being absorbed by its atmosphere. Astrometry as a method of hunting. A planet's gravity pulls its parent star out of place as it orbits. There is a possibility that a world is pulling on the star if it sways in a periodic rhythm. A telescope with exceptionally sharp vision can sometimes see the star moving back and forth in the sky. Using direct imaging for hunting. Because the stars are so bright and the planets so dim, it's challenging to capture a candid image of an extrasolar world. A mask called a coronagraph can sometimes block enough of the star's light to pick up a planet's dimmer reflected light. Microlensing by gravitational force. Whenever one celestial object passes in front of another, its gravity can bend and magnify the light behind it, making it appear brighter. The closer star will brighten twice if it has a planet. Comet crashes into the solar system. Comet Shoemaker-Levy 9 plunged into Jupiter's atmosphere in 1994, sending large plumes of debris into space. A spectacular view of the event was provided by Hubble, who watched the comet approach the collision site. As Jupiter's gravity shattered the comet into dozens of fragments, it observed violent waves erupting from the impact sites. Scientists believed it was a once-in-a-thousand-years event. Astronauts visited Hubble in May 2009 to install new instruments. In July, an amateur astronomer discovered a strange dark spot on Jupiter's surface as engineers and scientists tested and adjusted the refurbished telescope. As a result of an unnoticed asteroid impact, an expanding impact site has been left behind. Once again, the big world has been hit. 1994. First strike. The first comet, P. Shoemaker-Levy 9, which fragmented upon impact with Jupiter, produced a plume near Jupiter's limb. It was an important event that couldn't be missed. Hubble's team temporarily rearranged its schedule to take pictures of the impact site with one of its new instruments. Impacts of comets in visible and ultraviolet light. An asteroid struck Jupiter in July 2009, leaving a bruise the size of the Pacific Ocean. The Hubble Space Telescope observes different forms of light, allowing us to see more detail than we might otherwise. After a recent servicing mission, engineers interrupted the telescope's calibration to take a picture of the impact. As seen in visible light, Jupiter shows impact sites in its southern hemisphere. The same places on the planet are visible in an ultraviolet picture taken 20 minutes later. This image shows the comet's residue and materials thrown from Jupiter's lower atmosphere into its upper atmosphere by the impact, since the fine particles are easier to see in ultraviolet light. The images were taken on July 17, 1994. Images of Jupiter's impact sites raise questions about the planet's composition. The properties of the waves racing outward from Shoemaker-Levy 9 sites, for example, indicate that the planet's design is less similar to the Sun than researchers previously thought. Hubble's advantage is its ability to take high-quality images of such events on short notice, enabling us to deeply study our cosmic neighborhood. Given the short interval between results, one may wonder if these impacts are as rare as once assumed. Perhaps the timing of these incidents is coincidental, or perhaps collisions occur more frequently than we thought. Scientists once thought they had implications in our solar system that occurred thousands of years apart. NASA's Space Telescope. Since the dawn of astronomy, astronomers have shared one goal: to see more, see farther, see deeper. Humanity made one of its most significant advances in that journey thanks to the launch of the Hubble Space Telescope in 1990. The Hubble Space Telescope is one of NASA's most successful and long-lasting science missions. It is located above the atmosphere. It views the universe typically much better than ground-based telescopes. It has relayed hundreds of thousands of images back to Earth, shedding light on many of the great mysteries of astronomy. Named after a legend. Dr. Edwin Powell Hubble, an astronomer who made some of the most important discoveries in modern astronomy, is the name of the Hubble Space Telescope. Working with the most advanced technology at the Mount Wilson Observatory, Hubble showed in the 1920s that some of the numerous distant faint clouds of light in the universe were entire galaxies, much like the Milky Way. It changed the way astronomers viewed our place in the universe forever when they realized that the Milky Way was only one of many galaxies. Hubble's most important discovery came when, in 1929, he discovered that galaxies appear to move away from Earth faster the farther from Earth they are. The Big Bang theory posits that the universe began with a burst of energy at a single point and has been expanding ever since. Hubble Space Telescope cross-section. Hubble travels at about 5 miles per second, 8 kilometers per second, fast enough to cross the country in about 10 minutes during its orbit around Earth. Hubble's mirror captures light as it travels and directs it into its science instruments as it does so. A Cassegrain reflector telescope, such as Hubble, is a type of telescope. The main mirror or primary mirror reflects light. After being reflected by the primary mirror, the light is reflected by a secondary mirror. Using the secondary mirror, light is focused through a hole in the primary mirror, which is connected to the telescope's science instruments. It is a common misconception that the power of a telescope lies in its ability to magnify objects. A telescope works by collecting more light at a higher resolution than the human eye can see. The larger a telescope's mirror, the more light it can hold, and its vision is better. Hubble's primary mirror measures 94.5 inches, 2.4 meters. It is smaller than current ground-based telescopes, measuring 400 inches, 1,050 centimeters, but Hubble's location beyond the atmosphere gives it remarkable clarity. Following the light's capture by the mirror, Hubble's science instruments work together or individually to provide the observations. These instruments probe the universe in different ways. Hubble's functions are all powered by sunlight. Solar panels on Hubble convert sunlight directly into electricity. When the telescope is blocked from the sun's rays, some electricity is stored in batteries in Earth's shadow. Design of the Hubble Space Telescope. Wide Field Camera 3, WFC3, detects near-ultraviolet, visible, and near-infrared light, but not all at once. It is now Hubble's leading and most efficient camera. COS is a spectrograph that sees exclusively in ultraviolet light. Like prisms, spectrographs separate light from the cosmos into their component colors. A wavelength fingerprint provides information about an object's temperature, chemical composition, density, and motion. Advanced Camera for Surveys, ACS, sees the light in wavelengths from the far ultraviolet to near-infrared and is designed to study some of the earliest activity in the universe. ACS identifies the most distant objects in the universe, searches for massive planets, and examines the evolution of galaxies clusters. NICMOS is Hubble's near-infrared camera and multi-object spectrometer. The Space Telescope Imaging Spectrograph, STIS, is a spectrograph that sees ultraviolet, visible and near-infrared light and is known for its ability to spot black holes. COS can map out small objects like stars and quasars, but STIS can map out larger objects like galaxies. Working with Hubble's instruments. Hubble's primary camera, WFC-3, imaged NGC 6302 in ultraviolet and visible light with various filters to determine the properties of the nebular gas. It can observe objects hidden by interstellar dust, such as stellar birth sites, and peer into the deepest reaches of space using light which humans perceive as heat. Known as Fine Guidance Sensors, FGS, these sensors keep Hubble pointed in the right direction by locking onto guide stars. They can be used to measure stars' positions and motions precisely. Large Space Telescope Concept Art. In 1923, German scientist Hermann Oberth, one of the founders of rocketry, proposed blasting a telescope into space aboard a rocket. Lyman Spitzer Jr., an American astrophysicist, proposed a space observatory in 1946. During the next 50 years, he would devote himself to making this space telescope a reality. In 1969, NASA approved what was then called the Large Space Telescope Project. The original proposal was downsized to stay within budget, reducing the size of the telescope's mirror and the number of instruments it would carry. The team working on the project proposed a telescope with several interchangeable instruments. The telescope would either be returned to Earth for repairs and replacement instruments or serviced in space in orbit. Legends are made of this. Several decades before the Hubble telescope became a reality, legendary scientists considered the possibility of a space observatory. The European Space Agency, ESA, and NASA began working on a plan that eventually became the Hubble Space Telescope in 1975. To supply NASA with manpower and funding, ESA's support was crucial. NASA would provide the solar cells and one of the telescope's instruments, the Faint Object Camera. Congress approved funding for the telescope in 1977, after being reassured by the partnership. NASA centers and companies like Lockheed Missiles and Perkin-Elmer Corporation began working on the Hubble telescope piece by piece. The astronauts trained in a weightlessness tank in 1979 using a mock-up telescope to simulate Hubble Space Telescope construction. Lockheed Missiles and Space Company, Lockheed Martin, diagram of the Hubble Space Telescope. Hubble was scheduled to launch in October 1986. Tragically, the launch was delayed until January the 28th. Just over a minute after liftoff, the Space Shuttle Challenger exploded. Shuttle flights were suspended for 2 years. The telescope parts were stored. During the delay, Hubble workers continued improving solar batteries and upgrading other systems. Hubble was launched into orbit on April the 24th, 1990, aboard Space Shuttle Discovery. 5 instruments were carried by the telescope: the Wide-Field Planetary Camera, the Goddard High-Resolution Spectrograph, the Faint Object Camera, the Faint Object Spectrograph, and the High-Speed Photometer. Designed to be repaired and upgraded by astronauts in orbit, it would be needed sooner than later. Starting off on the wrong foot. It was clear almost immediately that something was wrong after Hubble entered orbit. The pictures were more explicit than those of ground-based telescopes, but they were not the new images promised. The photos were blurry. In Hubble's primary mirror, polished so carefully over an entire year, there was a flaw called spherical aberrations. The mirror was just slightly the wrong shape, which caused the light that bounced off the center of the mirror to focus differently from the light reflecting off the edge. This flaw, about 1/50th the thickness of a sheet of paper, was enough to distort the view. Hubble was the first instrument to come with built-in corrective optics. Scientists and engineers were faced with a well-known problem. Astronomers had been dealing with spherical aberrations since Galileo's time, but Hubble's mirrors could not be altered or replaced while in orbit. Fortunately, a solution was found. Mirrors could be used to intercept the light that reflects off the mirror, correct for the flaw, and bounce it to the telescope's science instruments. COSTAR, or Corrective Optics Space Telescope Axial Replacement, could be installed in place of one of the telescope's other instruments to correct their images. In addition to replacing the Wide-Field Planetary Camera, astronauts will install the Wide Field and Planetary Camera 2, WFPC-2, containing small mirrors to correct aberrations. As scientists and engineers worked, Hubble sent back images that, despite their flaws, still gave astronomers a better look than they'd previously had at the kind of cosmic phenomena Hubble was intended to reveal. Scientists developed new image processing techniques that partially recovered some of the information lost due to blurring. A planet-spanning storm churned on Saturn. The number of stars in Galaxy M87 revealed the scale of the supermassive black hole at its center. The lobes of gas emitted by the unstable, explosive supermassive star Eta Carinae were observed. The science Hubble accomplished with the problematic optics hinted at what could be accomplished with a fixed mirror. One of the most complex space missions was trained for 11 months by astronauts and NASA staff. Over 100 specially designed tools would be used in the repair process. It would be the first test of the telescope's vaunted capability of being serviced and repaired in space and its critical nature. The Space Shuttle Endeavour launched 7 crew members into orbit on December 2, 1993, for a mission that involved 5 days of spacewalks and repairs. The high-speed photometer was replaced with COSTAR. The Wide-Field Planetary Camera 2 replaced the original Wide-Field Planetary Camera. They also replaced solar panels, fuse plugs, and other hardware. They were finished on December 9th. Training for the first servicing mission. The Neutral Buoyancy Simulator simulates weightlessness by filling a vast water-filled tank with water. A view of the Indian Ocean shows the Space Shuttle Endeavour approaching the Hubble Space Telescope. NASA released the first images taken by Hubble's fixed optics on January 13, 1994. The photos were gorgeous, the resolution was excellent. Hubble finally became the telescope that had been promised. Pillars in the Eagle Nebula, M16A, one of Hubble's most famous images. Hubble's 1993 servicing mission was the first of many successful attempts to upgrade the telescope. Hubble received 2 gifts from the Space Shuttle in 1997, 2 instruments that featured technology not available when scientists designed and built the original equipment. New appliances gave Hubble a broader view of the cosmos, a pattern that repeated itself in the years that followed as astronauts brought Hubble improved technology. Astronauts would visit Hubble in 1997, 1999, 2002, and 2009. 3 of Hubble's 6 gyroscopes had failed, and Hubble needed at least 3 to observe a target. In November 1999, a 4th gyroscope failed, forcing Hubble into safe mode. Hubble was protected but could not keep its targets. In December 1999, Servicing Mission 3A was launched, followed 3 years later by Servicing Mission 3B. In 7 months, we developed, approved, and executed an urgent call-up mission. In Servicing Mission 3A, astronauts replaced all 6 gyroscopes and installed more powerful electronics, batteries, and new insulation. Hubble's Advanced Camera for Surveys, ACS, and a new power control unit was installed for Servicing Mission 3B. It was a delicate mission. Hubble had to be turned off for the first time since its launch to replace the power unit. The mission went well, and ACS, with its wide field of view, superb image quality, and exquisite sensitivity, brought 10 times more discovery power than the camera it replaced. An astronaut visit to Hubble in May 2009 was the culmination of a long effort to provide one more servicing mission to the telescope. The mission was initially scheduled for 2004. The view from Hubble improves over time. A Hubble image of a small region of the Orion Nebula reveals how the telescope's vision has improved over time. Hubble's fourth servicing mission was perhaps its most challenging and intense. As a result of the loss of the Space Shuttle Columbia, the mission was postponed until May. NASA approved a second shuttle mission after restarting the shuttle program and re-examining the risks. 2 weeks before the launch of the task in late September 2008, a malfunction occurred in a system that controls science instruments and directs data flow within the telescope. The problem was resolved by switching to a backup plan, but NASA was unwilling to leave the telescope without a spare. ACS and the Space Telescope Imaging Spectrograph (STIS) had already stopped working because of electrical malfunctions in 2007 and 2004. As part of Servicing Mission 4, astronauts installed a replacement data unit and performed on-site repairs for 2 failed instruments that had never been imagined by telescope creators. During spacewalks, astronauts had to crack into the interior of the instruments, replace components, and reroute power. In addition to Hubble's nail-biting repairs, 2 new advanced instruments, the Wide Field Camera 3 (WFC3) and the Cosmic Origin Spectrograph (COS), gave Hubble 5 tools for future observations. Hubble's latest workhorse instrument, WFC3, is susceptible and efficient, and it is capable of taking ultraviolet, optical, and infrared pictures. The COS spectrograph examines nearby stars, distant galaxies, and gas and dust. Space Shuttle Atlantis and the STS-125 crew launched on the final mission to upgrade Hubble on May 11, 2009. At first, NASA hoped Hubble could be brought back to Earth by the end of the task. Since SM-4 is likely to be the last astronaut mission to Hubble, astronauts installed a new device, the soft capture mechanism. In the future, when Hubble reaches the end of its life, a robotic spacecraft could attach itself to this device and guide it through its descent into Earth's atmosphere. Hubble will eventually cease to exist. Over the years, Hubble's components will gradually degrade to the point that the telescope stops functioning. When that happens, Hubble will continue orbiting Earth until its orbit decays, allowing it to spiral toward Earth. Getting ready for the future. While the shuttle released Hubble back into space in 2009, an imaging system called the Relative Navigation System (RNS) acquired images and video of the telescope's aft bulkhead. The artist's depiction shows one of the RNS cameras collecting data. Having this information will allow NASA to explore many options for a safe deorbit of Hubble. The replacement vehicle is unlikely to be able to return Hubble to Earth because it was explicitly designed to function with the space shuttle. Robotics will be used to help deorbit Hubble, guiding its remains through the atmosphere and into the ocean. Hubble's legacy, discoveries, trailblazing design, and success in showing us the universe in unprecedented detail will live on. Researchers will rely on Hubble's discoveries for years as they continue to understand the cosmos, a pursuit that has gained clarity, focus, and triumphs through Hubble's wealthy existence. Astronomical exploration of the universe will not end with Hubble's eventual demise. The James Webb Space Telescope, the successor to Hubble, will be the next giant observatory in space. The Webb Telescope, which will see infrared light, and the Hubble Telescope, visible light, will be tennis court-sized telescopes orbiting far beyond Earth's moon. The James Webb Space Telescope, beyond Hubble. In addition to the Hubble Space Telescope, the James Webb Space Telescope is NASA's next orbiting observatory. Webb will navigate through a frigid void nearly 1 million miles from Earth and peer back to when the universe was first illuminated by stars and galaxies. A stellar jet in Carina, visible versus infrared. Observations taken by Hubble in visible and infrared light reveal dramatically different and complementary views of an object. As Webb scans the cosmos, he will be looking for invisible radiation called infrared. Our ability to see infrared light is crucial to understanding the universe. The furthest objects we can detect are seen in infrared light. More spectacular objects that would otherwise be invisible emit infrared light, and infrared light passes through clouds of dust to allow us to see their depths. As Hubble sees visible light, Webb will see infrared clearly and precisely. Our view of a telescope is quite different from Webb's. This spacecraft has no tubes, only a tennis court-sized sunshield that blocks light from reaching its cold side, which houses its mirrors and science instruments. A box would interfere with faint infrared radiation going Webb's mirror and devices by trapping heat. The Webb telescope's 2-story high primary mirror is made of 18 segments of beryllium, which can withstand the extreme cold it will have to endure, minus 233.3 degrees Celsius. Webb will be the world's largest telescope. The primary mirror of the Webb telescope is too large to be monolithic, like Hubble's 94.5-inch, 2.4-meter mirror. Thus, its mirror is divided into 18 precisely ground and polished hexagonal segments. The giant telescope will have to be folded up inside the rocket that carries it into space. The mirror will unfold as it approaches its destination, and the sunshield will spread like wings. The vision of Webb will be able to detect features. Through Webb, infrared light will be visible because it will be stretched as it travels across space, a phenomenon known as redshifting. This will enable scientists to see the light from the first galaxies formed in the early universe. Infrared views from Webb will enable us to see through opaque clouds of gas and dust in our own galaxy to objects like newborn stars and dusty disks forming new solar systems, allowing us to better understand how stars and planets evolve. Webb's instruments will allow us to detect traces of water vapor from planets around other stars, possibly indicating the presence of life-giving oceans. Targets for Webb science. With Webb now in operation, and despite the high expectations for the telescope, the real excitement will come from Webb's discoveries. This simulated image shows what deep-field photos will look like with Webb. Far-reaching galaxies reveal new galactic populations. Astronomers will have an unprecedented tool to explore the cosmos once Webb takes its place among the stars. The science it reveals may, as with Hubble, lead to questions astronomers haven't considered yet. Webb's true strength may lie in its potential for unbounded, unexpected discovery. A cluster of stars, NGC 2074, in the Large Magellanic Cloud. Hubble observed a small nebula region near the star cluster NGC 2074, upper left. It is a firestorm of raw stellar creation, possibly caused by a nearby supernova explosion. The galaxy is about 170,000 light-years away near the Tarantula Nebula, one of the most active star formation regions in our local group. In the 3D image, we see dramatic ridges and valleys of dust, serpent-headed pillars of creation, and filaments of gas glowing under torrential ultraviolet radiation. It lies on the edge of a dark molecular cloud that is an incubator for new stars. Clusters of hot young stars born in NGC 2074 are eroding the nebula's wall with high-energy radiation. Another young collection may be hidden under a circle of brilliant blue gas at the bottom center. Another young cluster may be hidden. Retina Nebula, a seemingly square nebula, dying star IC 4406. Is it possible to make a square nebula form a round star? The conundrum is revealed when studying planetary nebula like IC 4406. IC 4406 is likely a hollow cylinder whose square appearance results from our vantage view. IC 4406 probably looks like the Ring Nebula when viewed from the top. Combining images taken by the Hubble Space Telescope in 2001 and 2002, this color composite picture represents the Hubble Space Telescope in representative color form. The cylinder's ends are filled with hot gas, while dark dust and molecular gas line its walls. Within the planetary nebula's center is the star that created this interstellar sculpture. IC 4406 will be nothing more than a fading white dwarf star in a few million years. NGC 3603 Star Cluster. Stellar Jewel Box is one of the most massive young star clusters in the Milky Way galaxy. Within the giant nebula NGC 3603, there are thousands of sparkling young stars. About 20,000 light-years away, NGC 3603 is a prominent star-forming region in the Carina spiral arm of the Milky Way. In this image, a young star cluster is surrounded by a vast area of dust and gas. It shows the stages of star formation. Sir John Herschel discovered the nebula in 1834. It spans roughly 17 light-years. Composite image of SNR 0509-67.5 taken with optical and X-ray imaging. A combination of data from two of NASA's great observatories was used to make this image of supernova remnant 0509-67.5. Hubble Space Telescope images of SNR 0509-67.5 and its surrounding star field are combined with Chandra X-ray Observatory images. We see a soft green and blue hue of heated material surrounding the glowing pink optical shell based on the X-ray data. This is a result of ambient gas being shocked by the expanding blast wave from the supernova. Bright areas of the X-ray data correspond to ripples in the shell. Eagle Nebula Gas Pillars, Messier 16. M16, or the Eagle Nebula, contains these towering tendrils of cosmic dust and gas. In this stunning Hubble image, the pillars of creation are part of an active star-forming region in the nebula and hide newborn stars within their wispy columns. It is not Hubble's first image of this iconic feature of the Eagle Nebula. However, it is the most detailed. Located just outside the frame, a cluster of young stars emits scorching ultraviolet light that bathes the pillars in light. Blue represents oxygen, red represents sulfur, and the green represents both nitrogen and hydrogen in the image. Winds from these stars are slowly eroding the towers of gas and dust. As a fascinating but relatively minor feature of the Eagle Nebula, which spans 70 by 55 light-years, the pillars of creation span approximately 4 to 5 light-years in length. The nebula was discovered in 1745 by Swiss astronomer Jean-Philippe Loy-de-Chaussure, located 7,000 light-years from Earth in the constellation Serpens. The Eagle Nebula can be seen through a small telescope and is best viewed in July when its apparent magnitude is 6. A large telescope and ideal viewing conditions are required to resolve the pillars of creation. The star-forming region S106. IRS-4, a massive star, is beginning to spread its wings. About 100,000 years ago, material streaming from this newborn star formed the nebula dubbed Sharpless-2 106 Nebula, S106, shown here. This nebula has an hourglass or butterfly shape due to dust and gas orbiting infrared source 4, IRS-4, visible in brown near the image center. Gas near IRS-4 emits light after ionization, while dust far from IRS-4 reflects light from the central star and functions as a reflection nebula. An infrared image of S106 reveals hundreds of low-mass brown dwarf stars buried in the nebula's gas. About 2,000 light-years away, S106 lies in the constellation of the Swan, Cygnus. The remnant of the supernova SN1006. Ancient supernova explosion creates a ribbon of light. A new star appeared suddenly in the sky in 1006 AD, witnessed and recorded by observers from Africa to Europe to the Far East. For several weeks, people could see the star without any aid during the day, and it remained visible for about 212 years before it faded away. This was probably the brightest star ever observed by humans. Scientists now know the object's true identity. SN1006 was a supernova that occurred about 7,000 light-years from Earth in the constellation Lupus. Over 1,000 years, the stellar explosion sent a blast wave racing through space at nearly 20 million miles per hour. Gas and dust in its path are being swept up and heated by the blast wave. There is a nebulous bubble about 60 light-years across surrounding the explosion site of this supernova. The star-forming region, 30 Doradus. At 160,000 light-years away, the Tarantula Nebula, 30 Doradus, is a bright and active star-forming region outside the Milky Way galaxy. 30 Dor contains the central cluster NGC 2070, the most dynamic region R136, which appears in the central right part of the image. This galaxy is a few million years old and contains thousands of young stars, including several of the largest. Bright blue stars are visible in the cavity excavated by stellar winds. Some redder stars are still embedded in the cloud material, seen in shadow except where illuminated by cavity stars. The embedded stars are more clearly visible in the infrared Hubble view due to the intervening cloud material. There is a nearby galaxy called NGC 602. Young stars in the small Magellanic Cloud are spewing radiation, eating away at the gas and dust cloud that gave birth to them. That scene can be seen in this Hubble image taken with the advanced camera for surveys. NGC 602 is a cluster of blue stars that developed when a large part of the gas cloud collapsed under gravity and became very dense. These hot young stars are currently producing fierce radiation, sculpting the inner rim of the gaseous nebula. The nebula's parts resist erosion better than others, leaving tall pillars that point toward the stars, the radiation source. It's relatively close to us, less than 200,000 light-years away, so it gives astronomers a chance to study star formation in a different galaxy. Additionally, it's a dwarf galaxy with fewer stars and lacks the enriched gas that more giant galaxies like ours possess. Therefore, it may provide a glimpse into what star formation might have been like in the early universe, NGC 6357 and Pismis 24. What is the maximum mass of an average star? Based on distance, brightness, and standard solar models, one star in the open cluster Pismis 24 was estimated to have more than 200 times the mass of our Sun, making it one of the most massive stars ever discovered. This star is the brightest object above the gas front in the featured image. However, the Hubble Space Telescope has revealed that Pismis 24-1's brilliant luminosity is not derived from a single star but from at least 3 stars. Component stars would still be among the most massive stars on record, with masses close to 100 solar masses. Stars are still forming in the emission nebula NGC 6357 at the bottom of the image. A spectacular cocoon of stars appears to be breaking out of what seems to be a Gothic cathedral. A Trifid Nebula. Charles Messier discovered the M20 in 1764. It is a star-forming nebula located 9,000 light-years from Earth in the constellation Sagittarius. M20, also known as the Trifid Nebula, has an apparent magnitude of 6.3 and can be seen with a small telescope. This is the best time to observe it. Hubble's image shows the center of the Trifid Nebula with its 3 wing-like bands of thick dust. Near the nebula center, we can see a group of recently formed massive bright stars. UV radiation from these stars dramatically influences the structure and evolution of the surrounding nebula. Star formation does not occur near these bright stars anymore because radiation has blown away the gas and dust from which new stars can form. As a result of the camera's design used to take the exposures, the image has a stair-step appearance. One of the 4 light detectors provided a higher resolution, but it had a smaller field of view than the other 3. Black regions were left when the images from all 4 detectors were combined because the detector with the higher resolution did not cover as much area as the others. Small Magellanic Cloud infant stars. For the first time, Hubble astronomers have identified a population of infant stars in the Milky Way satellite galaxy, the Small Magellanic Cloud, SMC, located 210,000 light-years away. Hydrogen fuel has not yet been ignited to sustain nuclear fusion. Its exquisite sharpness revealed a population of infant stars embedded in the nebula NGC 346 that are still forming from gravitationally collapsing gas clouds. The smallest of these infant stars is only half the mass of the Sun. Though starbirth is common in our galaxy's disk, this smaller companion galaxy is more primitive, as it lacks much of the heavier elements forged in successive generations of stars through nuclear fusion. As primitive building blocks of more giant galaxies, fragmentary galaxies like the SMC are considered primitive. When the universe was much younger, these galaxies were most common. The SMC offers a unique opportunity to study how stars formed in the early universe. The nebula NGC 346, nestled among other starburst regions within the small galaxy, contains more than 2,500 infant stars. Galaxy cluster Abell 520 merging. The image below depicts the distribution of dark matter, galaxies, and hot gas inside the core of the merging galaxy cluster Abell 520, formed through violent collisions of massive galaxy clusters. NASA's Hubble Space Telescope and the Canada-France-Hawaii Telescope took the natural color images of the galaxies. False-colored maps are superimposed on the image, showing the cluster's concentration of starlight, hot gas, and dark matter. From observations by the Canada-France-Hawaii Telescope, starlight from galaxies is colored orange. NASA's Chandra X-ray Observatory detected the green regions which show hot gas. This indicates that a collision has occurred. The blue areas indicate the bulk of the mass in the cluster, dominated by dark matter. Most of the universe's mass comprises dark matter, an invisible substance. The dark matter map was constructed using Hubble Wide-Field Planetary Camera 2 observations that detected how light from distant objects is distorted by the cluster of galaxies, an effect called gravitational lensing. There is a clump of dark matter near most of the hot gas in the center of the image, where few galaxies are found. The findings confirm previous observations of dark matter in the cluster. Fundamental theories of dark matter predict that galaxies should be anchored to dark matter, even during shocks of collisions. Hubble 1689, Hubble ACS-WFC. Hubble's latest image shows galaxy cluster Abell 1689. Hubble's Advanced Camera for Surveys, ACS, collected both visible and infrared data over a combined exposure time of over 34 hours, left image over 13 hours, right image over 20 hours, to show this patch of sky in greater and more striking detail than before. Golden clumps, bright stars, and ethereal spiral galaxies pepper this image. There are also several electric blue streaks circling and arcing around the fuzzy galaxies in the center. Material from some of these galaxies is being stripped away, giving the impression that they are bleeding into the surrounding space. Gravitational lensing is responsible for these streaks. Due to its massive size, Abell 1689 bends and warps the space around it, which affects the way light travels from objects behind the cluster. The streaks are the distorted forms of galaxies that lie behind the collection. NASA's great observatories study the galactic center. As part of the International Year of Astronomy 2009, NASA's great observatories, Hubble Space Telescope, Spitzer Space Telescope, and Chandra X-ray Observatory, have provided an unprecedented image of the central region of our Milky Way galaxy. In this spectacular image, infrared and X-ray light observations reveal the intense activity near the galactic core obscuring dust clouds. The image width covers about 1/2 of a degree, like the full moon's angular width. The galaxy's center is located just to the right of and below the middle of the image within the bright white region. Each telescope's contribution is displayed in a different color. Hubble's near-infrared observations are represented in yellow. In addition to revealing hundreds of thousands of stars, these observations highlight the regions where stars are being born. Spitzer's infrared observations are represented in red. From the radiation and winds of stars, glowing dust clouds are formed with complex structures, from compact spherical globules to long, stringy filaments. Gas is heated to millions of degrees by stellar explosions, and the supermassive black hole at the galaxy center emits X-rays. Chandra's X-ray observations are represented by blue and violet. On the left side is a bright blue blob, a neutron star or black hole emitting radiation. The composite image provides one of the most detailed views of our galaxy's mysterious core. Fornax Galaxy Field. Fornax, the furnace, is visible in the southern hemisphere sky on December evenings. Located in a bend of Eridanus, the river, Fornax is one of 14 constellations named by Nicolas Louis de Lacaille in the mid-17th century. It does not hold any exceptionally bright stars. Still, Fornax does save some treasures in its darker depths. At least 6 exoplanet systems. The Fornax dwarf galaxy, a satellite galaxy of our Milky Way. The Fornax cluster of galaxies, a cosmic filament showing the most considerable rotation in the universe. The fantastic Hubble Ultra Deep Field image. Galaxy M87's black hole emits a jet of high-speed electrons. Astronomers have detected particles being accelerated at speeds faster than 99% of the speed of light by the famous giant black hole in Messier 87 using NASA's Chandra X-ray Observatory. With observations of the massive dark object at the center of Galaxy Messier 87, or M87, the Event Horizon Telescope collaboration released the first image of a black hole in April last year. About 55 million light-years from Earth, this black hole has a mass of about 6.5 billion times that of the Sun. Astronomers have named the black hole M87, and it has recently been given the Hawaiian name Puwehi. Astronomers have observed radiation from a jet of high-energy particles blasting out of the center of M87 for years. Researchers have studied the jet in radio, optical, and X-ray light, including with Chandra. Chandra's observations have shown that sections of the jet are moving at nearly the speed of light. This is the first time such extreme speeds by a black hole's jet have been measured using X-ray data, said Ralph Kraft of the Center of Astrophysics, Harvard and Smithsonian in Cambridge, Massachusetts, who presented the study at the American Astronomical Society meeting in Honolulu, Hawaii. We needed Chandra's sharp X-ray vision to make these measurements. A cluster of lensing galaxies, Abell 383. There is so much dark matter mass in the giant cluster in the center of the image that its gravity bends the light of more distant objects. For very distant galaxies in the background, the cluster's gravitational field acts as a magnifying glass, turning and focusing the light towards Hubble. Astronomers can use gravitational lenses to extend Hubble's vision beyond what it would typically be capable of seeing. Additionally, the lensing effect can determine the distribution of matter, both ordinary and dark matter, within the cluster. Astronomers can study some of the very first galaxies in the universe in this way. Galaxy cluster CL0024+17, ZWCL0024+1652, dark matter ring. The blue map of the cluster's dark matter distribution shows a ring-like structure. It is superimposed on a Hubble image of the cluster. The ring is one of the strongest indications that dark matter, an unknown substance that permeates the universe, exists. Based on Hubble observations, this map shows how the cluster ZWCL0024+1652 distorts the light of more distant galaxies, an optical phenomenon called gravitational lensing. The universe's material is primarily made up of dark matter, which is believed to be its underlying structure. Even though astronomers cannot see dark matter, they can infer its existence by mapping the distorted shapes of background galaxies. Based on this mapping, we can determine the distribution of dark matter in the cluster. According to astronomers, two gigantic groups collided, forming the observed dark matter ring. Abell 2744, Pandora's cluster. At least 4 smaller clusters have piled up simultaneously to form Abell 2744, nicknamed Pandora's cluster. The collision occurred over 350 million years. Approximately 5% of the cluster's mass is occupied by galaxies. Around 20% of the gas is so hot it shines only in X-rays, red in the image. The cluster's invisible dark matter, which accounts for around 75% of its mass, is blue. The gravitational attraction of dark matter makes it apparent, as it does not emit, absorb, or reflect light. Using gravitational lensing, the team pinpointed the location of this elusive substance. The gravitational field created by the cluster bends light rays from distant galaxies. Images of galaxies in the background of Hubble and VLT observations show a series of telltale distortions. It is possible to map dark matter accurately by carefully analyzing how the images are distorted. Hubble WFC-3, Infrared Ultra-Deep Field. From 2003 to 2009, astronomers captured the Hubble Ultra-Deep Field (HUDF) images in visible and near-infrared light. Fornax is a constellation in the southern hemisphere seen in the HUDF. Astronomers have combined Hubble's colors using ultraviolet light to near-infrared. As a result of 841 orbits of telescope viewing, the resulting image contains approximately 10,000 galaxies extending back hundreds of millions of years to the time of the Big Bang. Moons of Saturn. The Hubble Space Telescope captured a picture of 4 Saturnian moons passing in front of their parent planet on February 24, 2009. Saturn's north polar hood is cast in a large shadow by the giant orange moon Titan. Near the ring plane and to the left of Titan is the moon Mimas, which casts a much smaller shadow on Saturn's equatorial cloud tops. The bright moon Dione and the fainter moon Enceladus are a little farther to the left, and off Saturn's disk is the bright moon Dione and the fainter moon Enceladus. As seen from Earth, these rare moon transits occur when Saturn's ring plane is near edge-on. Saturn's rings will line up precisely with our line of sight on August 10, 2009 and September 4, 2009. At that time, Saturn will be too close to the Sun to be seen from Earth. Ring plane crossings occur every 14 to 15 years. Hubble observed the ring plane crossing in 95-96 and several moon transits and helped discover several new moons of Saturn. The color of Neptune with satellites. Neptune is the 8th and most distant planet in our solar system, dark, cold, and whipped by supersonic winds. The only planet in our solar system not visible to the naked eye, Neptune is more than 30 times as distant from the Sun as Earth, and the first predicted by mathematics before its discovery. Since its discovery in 1846, Neptune finished its first 165-year orbit in 2011. View of Mars from Hubble, 8/2703. Within minutes of Mars's closest approach to Earth in nearly 60,000 years, NASA's Hubble Space Telescope captured this image of the planet. A series of exposures were taken between 5:35 a.m. and 6:20 a.m. on August 27th, using Hubble's Wide Field and Planetary Camera 2. The red planet is 34,647,420 miles away, 55,757,930 kilometers from Earth. This sharp natural color image has several prominent Martian features, including the largest volcano in the solar system, Olympus Mons, extensive canyons called Valles Marineris, an immense dark marking called Solis Lacus, and the southern polar ice cap. Located just above the center, Olympus Mons is an oval-shaped feature 3 times higher than Mount Everest. The dormant volcano is located in the Tharsis Bulge region, about as big as the US, and home to several extinct volcanoes. Just beneath Olympus Mons are the 3 volcanoes of Tharsis Montes. At the southernmost volcano, Arsia Mons, there are faint clouds. The moons of Pluto. On one of Pluto's moons, it might be difficult to tell when or from which direction the Sun rises each day. A detailed analysis of Hubble data shows that Pluto's moons Nix and Hydra wobble unpredictably. Moons wobble because they are embedded in a gravitational field that shifts constantly. Pluto and Charon are whirling around each other as they create this shift. Pluto and Charon are called twin planets because they share a common center of gravity located in the space between the bodies. It is strengthened by the football-like rather than the moon's spherical shape. The smaller moons tumble erratically due to their variable gravitational field. Pluto's other 2 moons, Kerberos and Styx, are likely in a similar situation. Ganymede and Jupiter, FPCC2 4907. With its Hubble Space Telescope, NASA captured Jupiter's moon Ganymede playing peekaboo with Jupiter. Ganymede can be seen just before it ducks behind Jupiter in this crisp Hubble image. Ganymede orbits Jupiter every 7 days. Ganymede's orbit is tilted nearly edge-on to Earth, so it can frequently be seen passing in front of and disappearing behind its giant host, only to reappear later. Ganymede is the largest moon in our solar system, composed of rock and ice. It is more significant than Mercury. Compared to Jupiter, the giant planet in our solar system, Ganymede looks like a dirty snowball. Jupiter is so prominent that only part of its southern hemisphere can be seen in this image. Astronomers can see features on Ganymede's surface thanks to Hubble, most notably Tros, the white impact crater and its system of rays, bright streaks of material blasted from the crater. TROS and its ray system are about the width of Arizona. Additionally, the image shows Jupiter's Great Red Spot, the prominent eye-shaped feature at the upper left. The Great Red Spot has been raging for more than 300 years and is the size of 2 Earths. Hubble's sharp image of the planet also reveals the texture of the clouds in the Jovian atmosphere and various storms and vortices. Moons and rings circling Uranus. Uranus's faint rings and some satellites are visible on this broader view. Brightness was enhanced outside Uranus to reveal soft rings and satellites. The brightest part of the outermost ring is on the lowest side, where it is more expansive. The dust and small pebbles create a thin, dark, and almost vertical line across the right side of Uranus, most visible on the natural color image. The bright satellite in the lower right corner is Ariel, which has a white surface. Outside the rings can be seen 5 small satellites with dark characters. They are Desdemona, Belinda, Portia, Cressida, and Puck from top to bottom. Deeper exposures of even fainter satellites were also taken in August 2003 with the advanced camera. Ceres, an asteroid-dwarf planet. Ceres is the largest object in the asteroid belt between Mars and Jupiter, and it is the only dwarf planet in the inner solar system. Giuseppe Piazzi discovered it in 1801 as the first asteroid in the asteroid belt. Ceres was the first dwarf planet to receive a visit from a spacecraft when NASA's Dawn arrived in 2015. Ceres, which has long been called an asteroid, is so much bigger and different from the rocky neighbors that scientists designated it a dwarf planet in 2006. Pluto is still 14 times more massive than Ceres, even though Ceres comprises 25% of the belt's mass. The Venusian cloud tops. On Venus, however, the clouds never part, for the planet is encased in a 20-kilometer thick layer of carbon dioxide and sulfur dioxide. Venus's cloud tops, as seen from 30,000 kilometers by the Venus Express spacecraft on December 8, 2011. Almost all the image shows the planet's southern hemisphere, with the South Pole at the bottom and the equator near the top. The top cloud layer visible in the picture is about 70 kilometers above the planet's surface. Venus's bright and dark markings are caused by variations in an unknown absorbing chemical at its cloud tops. This material is abundant in the low latitudes, upper part of the image, making this region appear dark in UV. Towards the brighter high latitudes, lower part of the image, the UV absorber is either insufficient or masked by a haze of a reflecting aerosol. The shapes of the cloud top features indicate vigorous circulation and dynamics in the planet's atmosphere. Saturn Aurora, January 28, 2004. This picture combined ultraviolet images of Saturn's southern polar region with visible light images of the planet and its rings. Solar particles collide with nitrogen and oxygen in the upper atmosphere to create auroral displays, primarily green and blue in color. Because of the ultraviolet light, the auroral show appears blue. As a result of glowing hydrogen in the atmosphere, the aurora would appear red to an observer on Saturn. Pluto's changing faces. Using multiple Hubble Space Telescope photographs from 2002 to 2003, this is the most detailed image ever created of Pluto's surface. Even though Hubble's view isn't sharp enough to see craters or mountains on the surface, it shows a complex and variegated world with white, dark orange, and charcoal black terrain. A dark, molasses-colored, carbon-rich residue is left behind when ultraviolet radiation from the distant sun breaks up the methane on Pluto's surface. A mysterious bright green spot appears at the center of the disk, 180 degrees, where there is an unusually high concentration of carbon monoxide frost. The New Horizons probe will photograph this region in the highest possible detail when it flew by Pluto in 2015. Global map of Jupiter. Hubble Space Telescope image of Jupiter's atmosphere reveals distinct bands of roiling clouds. This is a stretched-out view of the entire planet. Cloud bands parallel to the equator, currently orange in hue, are confined by jet streams that blow in opposite directions at different latitudes. There are a series of red oval-shaped cyclones embedded in the red swirling band of clouds above the equator. The white oval-shaped wind systems above this cloud band are called anticyclones. Cyclones are low-pressure areas, while anticyclones are high-pressure regions whose winds blow in the opposite direction of winds in cyclones. An oval-shaped string of white anticyclones, seen for decades, appears along with another latitude band in the planet's southern hemisphere. The Great Red Spot is slightly larger than the entire Earth and rotates counterclockwise. This image appears orange rather than red, with a small core of deep orange color in the center. Right to the left, clouds moving toward the giant storm are darker than in recent Hubble observations. There are whiter clouds to the south, moving towards the Great Red Spot from west to east. The Great Red Spot has been shrinking since the 1800s. It is springtime on Neptune. Neptune blooms in springtime. Neptune is the farthest and coldest planet among the significant planets. This might seem like an oxymoron. However, the Hubble Space Telescope has detected an increase in Neptune's brightness in the southern hemisphere. The increase in activity is considered a sign of seasonal change by astronomers. The Hubble Space Telescope observed in August 2002 that Neptune's brightness has increased significantly since 1996. This is due to increasing clouds in the planet's southern hemisphere. Increases in these numbers may result from seasonal changes caused by solar heating changes. In a 164.8-year orbit around the Sun, Neptune experiences seasonal solar heating because its rotation axis is angled 29 degrees to its orbital plane. Due to Neptune's distance from the Sun, the seasonal variation is 900 times smaller than on Earth. Neptune orbits the Sun every 165 years, so the rate of seasonal change is also much slower. Thus, spring will last for several decades in the southern hemisphere. This indicates that Neptune is responding to the weak radiation of the Sun. Hubble's Wide Field and Planetary Camera 2 recorded these images in visible and near-infrared light. Grand Design Spiral Galaxy M81. The American Astronomical Society released the sharpest image of the spiral galaxy M81. It is tilted at an oblique angle on our line of sight, giving us a bird's-eye view of the spiral structure. While the galaxy is similar to our Milky Way, our favorable view provides a better idea of spiral galaxy architecture. The Hubble Space Telescope can resolve individual stars in the galaxy, open star clusters, globular star clusters, and even luminous regions of fluorescent gas, even though it is 11.6 million light-years away. Spiral arms, which wind down to the nucleus, are formed by young, bluish hot stars in the past few million years. Additionally, they host a population of stars formed during a star formation episode about 600 million years ago. Dense green areas of star formation can be seen in the green regions. Clouds of hydrogen gas fluoresce due to the ultraviolet light from hot young stars. Sinuous dust lanes also wind into the nucleus of M81. The Hubble research shows that the mass of a galaxy's bulge is directly proportional to the size of the galaxy's black hole. The galaxy's bulge is much more prominent than the Milky Way. Much older, redder stars are found in the galaxy's central bulge. There is a 70 million solar mass black hole at the center of M81. The black hole is about 15 times bigger than the black hole in the Milky Way galaxy. Due to an encounter with a nearby spiral galaxy, NGC 3077, and a nearby starburst galaxy, M82, about 300 million years ago, M81 may be undergoing a surge of star formation along the spiral arms. Hubble's image will study the galaxy's star formation history and its relation to the neutron stars and black holes seen in X-ray observations made with NASA's Chandra X-ray Observatory, Hoag's Object Galaxy. Observe the Serpent constellation closely slithering through the northern sky, and you might see a galaxy within a galaxy within a galaxy. Astronomer Arthur Hoag discovered this cosmic turkducken in 1950, baffling astronomers. We are talking about a rare ring-shaped galaxy situated 600 million light-years from Earth and measuring 100,000 light-years across, slightly larger than the Milky Way. The oddball object was photographed by the Hubble Space Telescope and processed by geophysicist Benoit Blanco. The Hubble image shows a ring of billions of blue stars surrounding a much smaller and denser sphere of reddish stars. Another ring galaxy peeks out from behind the dark gap between the two stellar circles, much farther away from us. NGC 1275 image from Hubble ACS. Galaxy NGC 1275 shows the delicate thread-like structures in the surrounding gas. There are red filaments in the center of the Perseus galaxy cluster composed of cool gas suspended by a magnetic field and surrounded by 100 million degree hot gas. These filaments are dramatic markers of the feedback process that transfers energy from the massive black hole to the surrounding gas. As radio bubbles rise in the hot interstellar gas, cool gas is transported to the filaments from the galaxy's center. NGC 1275 is located in the center of the Perseus galaxy cluster and is one of the closest giant elliptical galaxies at a distance of 230 million light-years. 3 color filters were used to photograph the galaxy in July and August 2006. ARP 273, a rose of galaxies. The visualization of the interacting galaxy pair known as ARP 273 provides a unique three-dimensional view and serves as a visual reminder that astronomical images show objects that are spread across vast stretches of space. This movie combines the two-dimensional Hubble Space Telescope image with a more comprehensive ground-based image of the region around ARP 273. Through astronomy and computer graphics, a visual representation of a natural scene is created that cannot be experienced in person, but that inspires the imagination. A three-dimensional scene has been created by separating the foreground stars and background galaxies from the combined image. When possible, the shape and geometry of the interacting group are based on scientific knowledge and intuition and, where necessary, artistic license. NGC 1569, the Starburst Galaxy. The core of one of the most active galaxies in our local neighborhood, it is 5,000 light-years across. Millions of newly formed stars illuminate the galaxy called NGC 1569. NGC 1569 produces stars 100 times faster than our own Milky Way galaxy. Over the past 90 million years, this has been almost continuous. 3 giant clusters of stars, each containing more than 1 million stars, are at the core center. 2 clusters are so close together that they appear as one grouping. The clusters are situated within a large central cavity. Many massive young stars have already exploded as supernovae, blowing out the gas in the cavity. The explosions also triggered a violent flow of gases and particles that have formed giant gaseous structures. In the lower right, a sculpted structure is about 3,700 light-years long. These two giant bubbles of gas look like drifting islands. The largest bubble is approximately 378 light-years wide, while the smallest is about 119 light-years wide. Radiation from the young, bright stars within them illuminates them. Some of those stars can be seen peeking through their gaseous cocoons. Companion Galaxy M51 and Whirlpool Galaxy M51. M51's graceful winding arms appear like a grand spiral staircase that sweeps through space. The images taken with NASA's Hubble Space Telescope show a spiral galaxy's grand design, from its curving spiral arms where young stars live to its yellowish core which houses older stars. Known for its swirling structure, the galaxy is nicknamed the Whirlpool. Whirlpool's most recognizable feature is its two curved arms, a hallmark of so-called grand design spiral galaxies. Spiral galaxies have numerous loosely shaped arms that make their spiral structure appear less pronounced. Arms play an essential role in spiral galaxies. Compressing hydrogen gas, they create clusters of new stars. On the Whirlpool, the assembly line begins at the inner edge with the dark clouds of gas, then moves to the pink regions of star formation, and ends at the brilliant blue clusters of stars along the outer edge. Scientists believe the Whirlpool's prominent arms are due to a close encounter with NGC 5195, the yellowish galaxy at one of its outermost tips. The compact galaxy seems to be tugging at the arm at first glance. However, Hubble's clear view reveals that NGC 5195 is passing behind the Whirlpool. Millions of years have passed since the small galaxy passed by the Whirlpool. NGC 1300, a barred spiral galaxy. Within about 70 million light-years away in the constellation Eridanus lies the barred spiral galaxy NGC 1300. Hubble's composite image of the stunning island universe is the largest Hubble image of a complete galaxy ever taken. Hubble's image of NGC 1300 reveals striking details of NGC 1300's dominant central bar and majestic spiral arms. An examination of the classic barred spiral nucleus itself reveals a spiral structure region about 3,000 light-years across. NGC 1300, like other spiral galaxies, including our own Milky Way, is thought to have a supermassive black hole at its center. NGC 2841, the spiral galaxy. NGC 2841 shows a majestic disk of stars and dust lanes. A bright arc of light marks the galaxy's center. The dust lanes are silhouetted against the middle-aged population of whitish stars. Younger blue stars trace the spiral arms. The absence of pinkish emission nebulae suggests that new stars have not yet formed. Radiation and supersonic winds from young, super-hot blue stars probably cleared out the remaining gas, which glows pink, thus stopping further star formation in the areas where they were born. In contrast to other spirals ablaze with emission nebulae, NGC 2841 has a relatively low star formation rate. In the constellation Ursa Major, the Great Bear, NGC 2841 lies 46 million light-years away. The wavelengths of light range from ultraviolet to visible to near-infrared. Hubble's Wide-Field Camera 3 captured this image in 2010 using 4 different filters. Galaxy M82 Starburst. The Cigar Galaxy, also known as M82, appears bright at infrared wavelengths and is notable for its star formation activity. It experiences gravitational interactions with its galactic neighbor M81, causing it to have an extraordinarily high rate of star formation, a starburst. Young stars are born around the galaxy's center 10 times faster than inside our Milky Way. The radiation and energetic particles from these newborn stars carve into the surrounding gas, and the resulting galactic wind compresses enough gas to form millions of new stars. The accelerated rate of star formation in this galaxy will eventually self-limit. The process of star formation will destroy or consume the material necessary to create more stars if it becomes too vigorous. In tens of millions of years, the starburst will subside. German astronomer Johann Elert Bode discovered M82 and its neighbor M81 in 1774. M82 is a star 12 million light-years from Earth in Ursa Major's constellation. It has an observed magnitude of 8.5 and is best observed in April. Binoculars can see it as a patch of light, but larger telescopes are needed for a clear view of the galaxy's core. NGC 2207 and IC 2163 are spiral galaxies. Two spiral galaxies glide by each other like magnificent ships in the night sky in the direction of the constellation Canis Major. NASA's Hubble Space Telescope's Wide-Field Planetary Camera 2 captured images of the near collision. IC 2163 is the smaller galaxy on the right. NGC 2207 is the larger and more massive one on the left. The far-reaching tidal forces from NGC 2207 have distorted the shape of IC 2163, flinging stars and gas into long streamers stretching across 100,000 light-years. A team led by Bruce Elmer-Green and Deborah Elmer-Green performed computer simulations that demonstrate galactic collisions occur over a leisurely timescale. The National Science Foundation's Very Large Array Radio Telescope in New Mexico provides additional measurements which help reconstruct the collision based on the Hubble images. MAX 1206 – Gravitational Lens and Galaxy Cluster. The Hubble Space Telescope image shows the massive galaxy cluster MAX J1206. The cluster contains distorted images of distant background galaxies seen as arcs and smeared features. Gravitational lensing occurs when light from faraway galaxies is bent and magnified by the dark matter in the cluster. Astronomers can study distant galaxies that would otherwise be too faint to observe due to this phenomenon. Researchers measured the invisible glue that holds stars together within galaxies and makes up the bulk of the matter in the universe. A combination of visible and infrared light observations was taken by the Hubble Space Telescope in 2011. Stellar Fireworks Finale ranked first in Young Universe. Based on this artist's impression, an incredibly early universe, less than 1 billion years old, appears to have gone through a voracious onset of star formation, converting primordial hydrogen into many stars at an unprecedented rate. Compared to the sea of quiescent galaxies we see around us today, the sky would have looked very different back then. There are many starburst galaxies, but giant elliptical and spiral galaxies have yet to form. Starburst galaxies are filled with bright knots of blue stars that appear and disappear like fireworks. A torrent of ultraviolet radiation causes the regions of new starbirth to glow intensely red. Massive stars explode as supernovas and appear like a string of firecrackers across the sky. A starburst galaxy is sculpted with hot bubbles from supernova explosions and torrential stellar winds in the lower right. These galaxies have very little dust, since the heavier elements have not yet formed through nucleosynthesis. Hubble Space Telescope deep sky images support the theory that the first stars formed abruptly rather than gradually. Electrons and subatomic particles stream from the center of galaxy M87. One of nature's most amazing phenomena is the jet of electrons and other subatomic particles streaming out from the center of galaxy M87 like a cosmic searchlight. The blue of this jet contrasts with the yellow glow of billions of unseen stars that make up this galaxy. M87, NGC 4486, appears to be an ordinary elliptical galaxy, one of many ellipticals in the nearby Virgo cluster. Nonetheless, In 1918, astronomer H.D. Curtis noticed a curious straight ray emerging from M87. When the field of radio was blossoming in the 1950s, one of the brightest radio sources in the sky, Virgo A, was discovered to be associated with M87 and its jet. In the wake of these discoveries, decades of research have led to discovering the source of the jet's immense power. At the center of M87 is a supermassive black hole that has swallowed up a mass 2,500 million times the mass of our Sun. This jet is produced by the intense twisted magnetic fields trapped in the plasmas surrounding this black hole, and originates in the disk of superheated gas that swirls around it. Synchrotron radiation, electrons twisting along magnetic field lines in jets, produces the light we see and the radio emission, giving the jet its bluish tint. NGC 4038-4039, Antenna Galaxies. This is the sharpest image of the merging galaxies antenna taken by NASA's Hubble Space Telescope. As a result of the collision, billions of stars will form. The brightest and most compact starbirth regions are superstar clusters. A few 100 million years ago, two spiral galaxies began interacting, making the antennae galaxies one of the closest and youngest examples of galaxies colliding. The original galaxies consist primarily of old stars crisscrossed by filaments of dust, which appear brown in the image. Both galaxies are dotted with brilliant blue star-forming regions surrounded by glowing hydrogen gas, which appears in pink. In the antennae image, nearly half of the faint objects are young star clusters, containing tens of thousands of stars. The Crab Nebula, fragments in the heart. China's astronomers were startled by the appearance of a new star in 1054 AD, which was so bright for several weeks. On July 4, 1054, it exploded as a supernova. The Crab Nebula is visible today at the guest star location. Approximately 6,500 light-years from Earth, the Crab Nebula is the remnant of a star about 20 times as bigger as the Sun when it began. Hubble's Wide Field and Planetary Camera 2 acquired the Crab Nebula data in 1995. This false-color picture was created by combining 5 images taken with 5 different color filters. Unlike Jackson Pollock's abstract paintings, the image shows ragged shreds of gas expanding away at over 3 million miles per hour. Pulsars are neutron stars that revolve on their axis 30 times a second. In the Hubble image, the star's core is the lower of the two moderately bright stars to the upper left of the center. The ghostly diffuse bluish-green glowing gas cloud it produces in its vicinity and a blue arc immediately to its right results from heating its surroundings. Fireworks from space. Sheets of debris from a stellar explosion, N49 DEM-L190. These delicate filaments look like puffs of smoke and sparks from a summer firework display, but they are sheets of debris from a stellar explosion in a neighboring galaxy. It targeted a supernova remnant within the Large Magellanic Cloud, LMC, a nearby small companion galaxy to the Milky Way, observable from the southern hemisphere. N49, or DEM-L190, is the remnant of a massive star that died in a supernova blast thousands of years ago. Supernovae exploded billions of years ago in the Milky Way and left behind debris similar to our Sun and planets. The filamentary material will eventually be recycled into new generations of stars in the LMC. Hubble's giant mosaic of the Crab. NASA's Hubble Space Telescope took this mosaic of the Crab Nebula, a 6 light-year-wide remnant of a star's supernova explosion. Native Americans also recorded this violent event nearly 1,000 years ago in 1054. Most of the hydrogen in the orange filaments is left over from the star. As the dynamo driving the nebula's eerie interior blue glow, the neutron star embedded in its center rapidly spins. In the neutron star, electrons are whirling at nearly the speed of light around magnetic field lines. Due to the neutron star's rotation, it emits twin beams of radiation that pulse 30 times a second, like a lighthouse. An exploded star's neutron star is its crushed, ultra-dense core. A drawing of the Crab Nebula made in 1844 by Irish astronomer Lord Rosse gave its name, using a 36-inch telescope. As seen by Hubble and large ground-based telescopes like the Very Large Telescope of the European Southern Observatory, the Crab Nebula takes on a more detailed appearance that sheds light on a star's spectacular demise 6,500 light-years away. Streamers from nebula N44C flutter in stellar breeze. A region of glowing hydrogen gas surrounds an association of young stars in the Large Magellanic Cloud. Softly glowing filaments of light emanate from a complex of young stars, like the hair in Botticelli's famous portrait of Venus's birth. NASA's Hubble Space Telescope, HST, took this picture of N44C, a nebula. The Hubble Heritage Project presented this image taken with the Wide Field Planetary Camera 2 in 1996. Unlike other nebulae, N44C has a scorching star that illuminates it. Massive stars, between 10 and 50 times more massive than the Sun, have maximum temperatures ranging from 54,000 to 90,000 degrees Fahrenheit, 30,000 to 50,000 degrees Kelvin. N44C star appears to be significantly hotter, about 135,000 degrees Fahrenheit, 75,000 degrees Kelvin. Theories have been proposed to explain this unusually high temperature, including the possibility of a neutron star or black hole that intermittently emits X-rays, but has now switched off. Image of the Egg Nebula in rainbow colors. The Egg Nebula offers astronomers a unique look at the normally invisible dust shells surrounding an aging star, a rippling pool illuminated by underwater lights. The hidden star emits two beams of light that illuminate the pitch-black dust like a flashlight in a smoky room. These dust layers extend over 1/10 of a light-year away from the star and have a structure that forms rings around the star. A dust belt runs almost vertically across the image, blocking light from the central star. With the artificial Easter egg colors in this image, we can see how the light reflects off the smoke-sized dust particles and then travels towards Earth. During the day, dust in our atmosphere reflects sunlight so that only certain light waves get reflected to us. The same is true for reflections off water or roadways. Polarizing sunglasses use this effect to block out all reflections except those aligned with the polarizing filter material. It is like sliding a piece of paper under a door. For the paper to pass under the door, it must be parallel to the ground. Known as the Cat's Eye Nebula. NASA's Hubble Space Telescope captured this new, detailed view of the Cat's Eye Nebula, NGC 6543, a bullseye configuration of 11 or even more concentric rings or shells around the cat's eye. Rather than being rings, each ring is the edge of a sphere projected onto the sky. That is why it appears bright along its outer edge. According to observations, the star ejected its mass in a succession of pulses every 1,500 years. Dust shells created by these convulsions contain as much mass as all the planets in our solar system collectively, still only 1% of the mass of the Sun. Concentric shells form an onion-like structure around the dying star. Hubble's view is similar to splitting an onion in half, where each layer can be seen. Astronomers were surprised to see bullseye patterns around planetary nebulae, as they did not expect that periods of mass loss at the end of stellar lives would repeat every 1,500 years. Many possible explanations have been proposed, including magnetic activity cycles like our Sun's sunspot cycle, companion stars rotating around the dying star, and stellar pulsations. Another theory is that the outflowing material is smooth and the rings are formed later due to the waves. Helix Nebula. A dying star is exhibiting a cosmic tantrum. The star's outer dusty layers unravel into space during death, glowing from the intense ultraviolet radiation emitted by the hot stellar core. Around 650 light-years away in the constellation of Aquarius is the Helix Nebula. It is typical of a class of objects called planetary nebulae, also known by the catalogue number NGC 7293. Their resemblance to gas giant planets led to their false name when discovered in the 18th century. Astronomers believe that planetary nebulae were once stars that looked a lot like our Sun. These stars transform hydrogen into helium in their cores in massive runaway nuclear fusion reactions. All of our Sun's light and heat comes from this fusion process. When our Sun dies in about 5 billion years, it will become a planetary nebula. When the hydrogen fuel for fusion reaction runs out, the star turns to helium for fuel, burning it into an even greater mix of carbon, nitrogen, and oxygen. The star will also exhaust its helium, displacing its outer gaseous layers and leaving behind the tiny, hot, dense core, known as a white dwarf. Despite being about the size of Earth, the white dwarf has a mass very similar to that of the initial star. In fact, a teaspoonful of a white dwarf would weigh as much as a few elephants. An intriguing feature of planetary nebulae is that they appear remarkably similar across various wavelengths, from ultraviolet to infrared. The helix is recognizable at any wavelength, but the combination shown here emphasizes subtle differences. MYCN18, a planetary nebula. Image of MYCN18, a young planetary nebula about 8,000 light-years away, taken with NASA's Hubble Space Telescope, HST. Hubble's image reveals that MYCN18 is an hourglass with intricate etchings on its walls. This picture was composed of 3 images taken in the light of ionized nitrogen, represented by red, hydrogen, green, and doubly ionized oxygen, blue. These results shed new light on the poorly understood ejection of stellar matter accompanying the slow death of Sun-like stars. Based on previous ground-based images, MYCN18 appears to be a pair of large outer rings and a smaller central ring, but the fine details are not visible. MYCN18, as revealed by Hubble, does not meet some crucial theoretical expectations. The hot star, which is supposed to eject light from the nebula and lie at its center of symmetry, is off-center. On closer inspection, an apparent bright elliptical ring at the center, which might be mistaken for an equatorially dense region at first sight, is revealed to be a potato-shaped structure with a symmetry axis significantly different from that of the enormous hourglass. NGC 2392, the Eskimo Nebula. NASA's Hubble Space Telescope captured its first glimpse of the heavens after its successful December 1999 servicing mission showing a planetary nebula, the glowing remains of a dying star. William Herschel first spotted NGC 2392 in 1787. The inner nebula also contains intriguing details. While the bright central region resembles a ball of twine, it is a bubble of material blown into space by the central star's high-speed wind. A dying star is surrounded by 2 elliptically shaped lobes of matter that stream above and below it. One bubble partially obscures the second lobe in this photo because it is positioned in front of another. The red rectangle. Dying star HD 44179. They may not have seen the fabled stairway to heaven, but they have captured something fascinating: ladder-like structures encircling a dying star. An image taken with NASA's Hubble Space Telescope reveals startling new details about one of the Milky Way's most unusual nebulae. HD 44179 is also known as the red rectangle due to its unusual shape and color, as seen with ground-based telescopes. Hubble has revealed many new features in the red rectangle that could not be seen from Earth by ground-based telescopes. The Astronomical Journal published details of the Hubble study in its April 2004 issue. Hubble's sharp pictures reveal that the red rectangle is not really rectangular, but instead has an overall X-shaped structure that the researchers attribute to outflows of gas and dust from the star at its center. A star's outflows eject in opposing directions, producing the appearance of two ice cream cones touching at their tips. This nebula is also remarkable for its straight features that resemble ladder rungs, making it resemble a spider web, unlike any other nebula we know of. These rungs may have formed every few hundred years during episodes of mass ejection from the star. As a series of nested, expanding structures, they could resemble wine glasses seen exactly edge-on, so their rims appear as straight lines. As the dying star flung material into space, the planetary nebula began forming about 10,000 years ago. Nebula Spirograph, IC 418. The star in the middle of IC 418 was a red giant, but then it ejected its outer layers into space, producing the nebula, which has a diameter of about 0.2 light-years. From the hot core of the red giant, the stellar remnant at the center emits ultraviolet radiation, causing the surrounding gas to fluoresce. For millions of years, the nebula will gradually cool and fade away as a white dwarf. IC 418 was likely like our Sun only a few million years ago. The Sun is expected to undergo a similar fate, but fortunately, this will not happen for 5,000 million years. Perhaps they are caused by chaotic winds from the central variable star, which changes brightness unpredictably in just a few hours. Extrasolar planet HD 189733b, as seen by an artist. A hot Jupiter-class planet is shown orbiting its yellow-orange star HD 189733. NASA's Hubble Space Telescope measured the planet's visible light color, deep blue. It is not due to oceans, but to the effects of a 2,000-degree atmosphere where silicate particles melt to form raindrops of glass that scatter blue light more than red light. HD 189733b was found in 2005 and is only 2.9 million miles away from its parent star. The planet is gravitational tidally locked, so that one side always faces the star and the other is permanently dark. In 2007, NASA's Spitzer Space Telescope created a thermal map that revealed the presence of a hot spot on Earth in the early afternoon. The high-altitude clouds laced with silicates may blow from the day side to the night side at 4,500 miles per hour. The planet is only 60 light-years from Earth. Alpha Centauri, the closest star to our Sun, appears as two faint stars near the center of the image. HH-110 Cosmos Skyrocket. The Herbig-Haro 110 is a geyser of hot gas ejected from a molecular hydrogen cloud. Photo from the Hubble Space Telescope shows plumes that are light-years across. While gas plumes appear to be smoke, they are billions of times less dense than the smoke from a July 4th firework. There is a wide variety of Herbig-Haro HH objects, but the basic configuration remains the same. Streams of heated gas are ejected in opposite directions away from a forming star. Scientists suspect that these outflows are fueled by gas accreting onto a young star surrounded by a disk of dust and gas. Using a disk as a fuel tank, a star as a gravitational engine, and jets as an exhaust. It is like a traffic jam on the interstate when these energetic jets collide with colder gas. The gas slows to a crawl within the shock front, but more gas piles up as the jets continue to slam into the shock from behind. The curving, flaring region begins to glow when the temperature rises sharply. As the name implies, bow shocks resemble the waves that form at the front of a boat. HH 901 Mystic Mountain Jet Detail. This close-up series shows the complex gas structures in a small portion of the Carina Nebula. A nebula is a cloud of predominantly hydrogen gas. Due to its dusty composition, the cloud is opaque. An ultraviolet gusher originating from a young star is eroding the cloud. The animals sculpt a variety of fantasy shapes, some resembling tadpoles. The 2.3 trillion mile-long structure at the upper right is a small piece of nebulosity freely drifting in some frames. In the upper left frame, there is a 3.5 trillion mile-long horizontal jet. A star hidden at the tip of the pillar-like structure is blasting it into space. A bow shock has formed near the jet's tip. Illustration of exoplanet HD 189733b, artist's rendition. In this artist rendering, HD 189733b's atmosphere is shown evaporating due to a powerful eruption from its star. Concept art of the exoplanet OGLE 2005 BLG 390LB. Located near the center of our galaxy, the Milky Way, this exoplanet is around 25,000 light-years away from Earth. It orbits its parent star every 10 years, and is about 3 times as far away as Earth is from the Sun. Concept of an exoplanet orbiting Fomalhaut. It shows the newly discovered planet Fomalhaut B orbiting its Sun. Around Fomalhaut B is a structure mainly made of brown and gold colors. A Saturn-like ring may encircle the planet, say astronomers. A material ring also surrounds Fomalhaut. An edge of this vast disk is shown in the background as a cloud-like feature that intersects the 200-million-year-old star. Fomalhaut B is located 1.8 billion miles inside the disk's inner edge. Every 872 years, the planet completes an orbit around Fomalhaut. Gliese 876, a giant red dwarf star orbiting the Earth. New Hubble Space Telescope measurements of the star's wobble, caused by the planet's gravitational pull, have confirmed that the planet's mass is approximately twice that of Jupiter. There is only 1/5 the distance between the planet and the star between the Earth and the Sun. As the planet is too far away to be photographed by modern telescopes, it is probably a gas giant world possibly encircled by moons, as depicted in this illustration. As estimated by earlier ground-based observations, Gliese 876 also contains an inner planet with a mass half that of Jupiter. The inner gas planet in the system appears like a bright star near the red dwarf. Despite its proximity to Earth, the red dwarf star is too faint to see with the naked eye. Its mass is 1/3 that of our Sun. WFC3 Planetary Nebula NGC 6302. Located roughly 3,800 light-years away in Scorpius, NGC 6302 is a spectacular planetary nebula. More commonly known as the Bug Nebula or Butterfly Nebula, this celestial object resembles a delicate butterfly. The dainty-looking wings are roiling regions of gas heated to over 36,000 degrees Fahrenheit. Gases are hurling through space at 600,000 miles per hour. Expelled over about 2,200 years, the blowing gas represents the star's outer layers. Approximately half the distance from the Sun to the nearest star, Alpha Centauri, is covered by the butterfly. Towards the center of this fury is a dying star that was once about 5 times the mass of the Sun. Having ejected its gaseous envelope, it emits ultraviolet radiation, making the cast-off material glow. When viewed through a small telescope, this object is an example of a planetary nebula, which is named because many of them appear round like planets. A donut-shaped ring of dust, or torus, surrounds the star, hidden within the nebula's center, and appearing as a dark band that pinches it. Several planetary nebulae display the classic bipolar or hourglass shape owing to the thick dust belt surrounding the star. NGC 1309, ACS, a pinwheel-shaped galaxy. NASA's Hubble Space Telescope recently observed this dramatic spiral galaxy. A color image of NGC 1308, an upright spiral galaxy, is captured with stunning details. SN 2002FK, whose light reached Earth in September 2002, was located in NGC 1309. NGC 1309 is located 100 million light-years, 30 megaparsecs. About 200 galaxies make up the Eridanus group of galaxies. Trapezium Cluster of Orion, NICMOS. The NASA ESA Hubble Space Telescope uncovered a swarm of newborn brown dwarfs deep within a stellar nursery. Near-infrared images from the orbiting observatory's near-infrared camera showed approximately 50 of these objects in the Orion Nebula's trapezium cluster about 1,500 light-years away. An image taken by the Hubble telescope's Wide Field and Planetary Camera 2 cannot see brown dwarfs because they are too dim. As with the near-infrared image, this view does not show the assemblage of infant stars. This is because dense clouds of dust and gas surround young stars. Using its near-infrared camera and multi-object spectrometer, Hubble's near-infrared telescope captured images of those objects through the clouds. Investigating doomed star Eta Carinae, STIS. For decades, astronomers have been enchanted by the signature balloon-shaped gas clouds blown from two massive stars called Eta Carinae. Eta Carinae has exhibited violent outbursts due to her volatile temperature over the past 200 years. The newly repaired Space Telescope Imaging Spectrograph, STIS, aboard NASA's Hubble Space Telescope, has discovered a stream of charged particles emanating from a massive stellar wind and some of the chemical elements emitted during the eruption in the middle of the 19th century. Chemical information was resolved along a narrow section of one of the giant lobes of ejected material using STIS. In the resulting spectrum, iron and nickel define the outer material cast off from Eta Carinae in the 19th century. The STIS also reveals the interior material being carried away by the wind from Eta Carinae, the primary star. A sun's worth of mass is carried away by the wind every 1,000 years. The Pleiadae and HST field of view, FGS. The stars in this image are members of the Pleiades, or Seven Sisters, an open star cluster. Hubble's fine guidance sensors refined the distance to the Pleiades to about 440 light-years. Hubble's field of view includes the fine guidance sensors. A circumference approximately equal to the angular size of the Moon is traced. They are superimposed on this image to give a sense of Hubble's very narrow view of the heavens. Eagle Nebula, Messier 16. M16, or the Eagle Nebula, is dominated by towering tendrils of cosmic dust and gas. This is not Hubble's first image of this iconic feature of the Eagle Nebula, but it is the most detailed. Blue represents oxygen, red represents sulfur, and the green represents both nitrogen and hydrogen. A cluster of young stars emits scorching ultraviolet light outside the frame to bathe the pillars. Eventually, the dust and gas are being eroded by the winds of these stars. In addition to spanning roughly 4 to 5 light-years, the pillars of creation represent a fascinating but relatively minor feature of the Eagle Nebula, which spans 70 by 55 light-years. This nebula was discovered in 1745 by Swiss astronomer Jean-Philippe Loy-de-Chausseux. It is possible to see the Eagle Nebula through a small telescope with an apparent magnitude of 6. Pillars of creation can only be resolved with a large telescope and optimal viewing conditions. Nebulae of Orion. The Maya believes M42 of Mesoamerica to be the cosmic fire of creation. It is located in the constellation Orion. Throughout human history, many different cultures have known this stellar nursery as the Orion Nebula. 1,500 light-years away, the nebula is the nearest sizable star-forming region to Earth, with an apparent magnitude of 4. M42 can be seen with the naked eye due to its brightness and prominent location below Orion's belt, while its stellar birth is visible with telescopes. It is best observed in January. The Maya culture compared the Orion Nebula to a cosmic fire of creation. 4 massive young stars form the nebula's bright central region. 4 big stars are called the trapezium because they are arranged in a trapezoidal pattern. Ultraviolet light emitted by these stars is carving a cavity in the nebula and disrupting the growth of hundreds of smaller stars. Hubble's image of the Orion Nebula is the sharpest ever taken. This mosaic was created from 520 different Hubble exposures in multiple wavelengths of light. In the image, orange represents hydrogen, green represents oxygen, red represents sulfur, and observations are made with infrared light. Hubble captured most of the nebula, but ground-based images filled the gaps. Globules of Thackeray. Beautiful and remarkable images taken by NASA's Hubble Space Telescope show strangely glowing dark clouds. Dense, opaque dust clouds, called globules, are silhouetted against nearby bright stars in the active star-forming region IC 2944. The globules were first discovered in IC 2944 by astronomer A.D. Thackeray in 1950. Omega Centauri, the core of the globular cluster. Using NASA's Hubble Space Telescope, scientists have peered into the heart of a dense swarm of stars called Omega Centauri. Omega Centauri, a massive globular star cluster located some 17,000 light-years from Earth, contains several million stars in locked orbits around a common gravitational center. Ground-based telescopes have difficulty making out individual stars because the cluster's core is packed so densely with stars. As a result, Hubble's high resolution can pick up where ground-based telescopes leave off, capturing distinct points of light from stars at the cluster's center. M100 galaxy. M100 is an excellent example of a spiral galaxy with a grand design. The Hubble image shows individual stars within the galaxy's prominent spiral arms. The dusty structures swirl around the galaxy's nucleus and are characterized by a flurry of star formation. Additionally, M100's characteristic arms contain several small black holes, including the youngest ever observed in our galaxy. In 1781, the French astronomer Pierre Méchain, Charles Messier's fellow comet hunter, spotted the galaxy and discovered 8 comets in his lifetime. Despite its distance from Earth, M100 appears dim in the night sky. At the same time, it can be observed through small telescopes. Its apparent magnitude of 10.1. The galaxy can be observed in greater detail with larger telescopes. During May, you can observe M100 in the constellation Coma Berenices. Because of the camera's design, the image has a stair-step appearance. One of the 4 light detectors on the camera had a higher resolution but a smaller field of view than the other 3. Since the detector with the higher resolution does not cover as much area as the other 3, when the images from all 4 detectors are combined into one picture, there will be black regions. This is the Cygnus Loop Nebula. The Cygnus Loop, the Veil Nebula, is a remnant of a supernova explosion about 10 to 20,000 years ago. Modeling its spectacular filamentary shape suggests the explosion was inside an interstellar cavity created by the progenitor star. Many of an object's physical properties are uncertain in astronomy due to its distance. Recent distance estimates have ranged over a wide range, generally consistent with this one, though the most commonly quoted value is a 2005 measurement between 1,500 and 2,100 light-years. The past 2 decades have seen astronomers attempt to pin down the distance by measuring the distances to nearby stars, measured as absorption lines from the nebula in their spectra. But the distances to those stars are also uncertain, and parallax measurements of some of the stellar distances have also been unreliable. Recent efforts have also been made to measure the distance by observing the motions of the nebula gas directly, estimates suggesting a distance of 2,600 light-years, which is consistent with the old value of 2,500 light-years.
In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. And it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out, communication streams were cut, airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives, our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
Three, two, one, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood. The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun. If we want to understand the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space probes scan and study the sun in ways we never imagined, even 30 years ago. By studying the sun from the vantage of space, we can see it in a whole new light, using different light wavelengths, including X-ray and extreme ultraviolet. We can peel back its layers and begin to understand how and why the sun acts the way it does.
The different wavelengths mean different temperatures, and different structures are more visible in different wavelengths than in others.
Our robotic space probes never stop watching the sun. With their help, scientists are working out the big questions about our star, and we already know a lot. The sun is one of over 200 billion stars in our Milky Way galaxy, but it is our closest at 93 million miles away from Earth, almost the same distance as 4,000 trips around the globe. And despite that distance, its light only takes 8 minutes to reach Earth. It is only 4.5 billion years into its nearly 10 to 11 billion year lifespan. And though technically a medium-sized star called a dwarf, it is enormous, 900,000 miles across, and if hollowed out, 1.3 million Earth-sized planets could fit inside. The Sun accounts for 99.8% of the mass in the solar system, and it weighs 300,000 times more than the Earth. It is made up almost entirely of a superheated form of electrified and magnetized gas called plasma. The Sun packs enough gravitational pull to keep the planets from spinning off into space. And as Copernicus first suggested, it rules the center of our solar system with a gravitational iron fist.
Copernicus's model, in which he placed the Sun in the middle of the solar system with all the planets going around it, instead of everything going around the Earth, was a giant paradigm shift. It meant that the Sun is the most important thing in the solar system. It meant that we really should understand the Sun.
Our Sun, like all other stars in the universe, is made from the dust of stars that lived and died over billions of years, going all the way back to the Big Bang.
So our Sun and our solar system is really the debris from many generations of stars.
The Sun we see every day is the solar system's source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and is the engine that drives it all.
Inside the Sun's core, the process of fusion is occurring, and that fusion process is giving off light and particles.
Every second the Sun shines, it releases the same amount of energy as 1 million H-bombs. The Sun's light is made of particles called photons, born in the core, then propelled by convection currents through the radiative and convective zones of the Sun. Eventually, they reach the volatile outer layers of our nearest star.
The Sun's outer parts consist of 3 regions. There's the photosphere, or surface of the Sun, and it's not really a hard surface like that of the Earth. The Sun is gaseous throughout. And the temperature of the photosphere is around 10,000 degrees Fahrenheit.
Above the thin layer of the photosphere is another thin layer called the chromosphere. And the chromosphere is slightly hotter than the photosphere, which is counterintuitive because you would think that as you go away from the source of all the energy and heat, the core, that temperature would drop. But in fact, the temperature rises from the photosphere to the chromosphere. And it gets even hotter as you rise to the third layer of the atmosphere called the corona.
And then beyond the chromosphere is a large, tenuous, extended region, the corona, which is millions of degrees.
The Sun produces a continuous outward flow of energy called the solar wind. Constantly blowing, it carries energy out into the solar system, extending our Sun's reach 9.3 trillion miles, well beyond Pluto.
The space in between the planets and the space in the entire solar system is not an empty void, but it's full of these particles and it's full of these rays of light.
While the solar wind blows away from the Sun, its gravity holds and pulls everything in. Take comets. All comets orbit the Sun and can get pulled directly into the line of fire. Recently, scientists witnessed one of the Sun's most dramatic outbursts, a coronal mass ejection, ripping the tail off a comet.
When it hit the comet, the tail was cut off like you took a knife, and the tail drifted away. And then it took a little more time for the comet to generate more gas and plasma and dust and create a tail. It tells us about how the solar wind moves in the solar system and how it can affect things.
The Sun affects everything it touches, even us. To learn just how much, scientists sometimes rely on a remarkable cosmic coincidence. The lethal output of the Sun has made studying it almost as difficult as understanding it. But scientists can get a good look at our nearest star thanks to a cosmic coincidence. A total eclipse of the Sun.
A total solar eclipse occurs when, from our perspective, the moon is exactly aligned with the Sun and blocks its photosphere. It's a glorious sight.
The solar eclipse is the most wonderful thing to see. It grows really dark by factors of thousands within seconds. And as it does become so dark, You can look up in the sky, you see the dark shadow coming from one direction, sweeping at you. It's really coming at thousands of miles an hour. So it's very impressive to see.
Humankind has marveled at the mysteries of the eclipse for millennia. Scientists have used it as an opportunity to see the sun's outer atmosphere, the enigmatic corona. One of the hottest regions of the sun, energy from the corona radiates out to the edge of the solar system.
The entire solar system actually sits in this outer corona of the sun. So this atmosphere of the sun is bathing all the planets.
The engineers who built the Solar and Heliospheric Observatory, or SOHO, installed an artificial eclipse into the space probe. Called a coronagraph, it does the same thing as a natural eclipse, blocking out the blinding rays of the sun, so scientists can try and answer an old question.
How does the solar corona get so hot? After all, the everyday surface of the sun, the photosphere, is only around 10,000 or a little more Fahrenheit, and the corona, on the other hand, is millions of degrees hot. If you go away from a stove, you know it gets cooler, but if you go away from the everyday surface of the sun, it gets hotter. And how is that?
It all starts at the sun's core, where every second, nearly 700 million tons of the universe's most common element, hydrogen, are converted into helium through nuclear fusion, giving off the energy that becomes photons, otherwise known as light.
The sun's core is really hot, several tens of millions of degrees. And there, the temperatures are so high that protons, hydrogen nuclei, can come together, grab each other, fuse, eventually into helium, and in this way, release energy.
What happens with these photons, they go through this process, what we call a random walk, where they have to go through the layer of the sun, they get absorbed and then reabsorbed into lots of different photons at lower energy level. So this process of being absorbed and reabsorbed millions of times can take 150,000 years.
Once out of the sun's interior, photons are only 8 minutes away from Earth, but they're leaving behind a world in constant motion. The solar surface boils. Energy rises constantly from below. Coils of plasma and energy, called coronal loops, spring across the sun. While dark regions known as sunspots stretch thousands of miles, and at only 7,000 degrees Fahrenheit, these sunspots are the coolest part of the sun, emitting less light than the surrounding area.
If you were to pluck a sunspot away from the sun and place it in the sky, it would actually be as bright as the full moon.
Sunspots appear on the surface and are easy to see. Their genesis, however, is tied to the sun's deep interior and complex rotation.
The sun doesn't rotate like a solid body. Instead, it rotates more quickly near the equator than near the poles, which leads to sunspots. The equator completes one rotation in 25 days. Mid-latitudes complete one rotation in about 30 days, and near the poles, one rotation is completed in about 35 days.
Called differential rotation, this process makes the sun's interior churn at different speeds, creating intense magnetism in the form of millions of magnetic field lines, which get mixed up as the sun's interior twists up like a rubber band.
This builds up pressure, which makes them buoyant. So they float to the surface, and where they pop through the surface, they create sunspots.
Once on the surface, the now twisted and balled up magnetic field lines block the convection of superhot plasma from rising, making sunspots appear dark.
And when those sunspots start to twist around, you can imagine that you have one sunspot here and one sunspot here, and there's a magnetic field that connects the two. And that magnetic field gets twisted, and eventually the same sort of thing that happens with a rubber band, it pops. When the magnetic field pops, it releases energy. And in the case of the sun and solar flares, it releases huge, huge amounts of energy.
The magnetic field lines created by the twisting and churning of sunspots, though invisible, can be seen in the dramatic formations on the surface of the sun, in the form of flares and prominences. It is here that the sun's influence starts, as the breaking of these magnetic field lines drives massive amounts of energy from our nearest star out into the solar system. And it is these magnetic field lines that are behind most theories on why the corona is so much hotter than the surface.
It's pretty clear that it has something to do with the magnetic field that heats the corona. But presumably there are waves along the magnetic field that bring energy from underneath the surface of the sun into the corona.
The solar probe Hinode, which means sunrise in Japanese, was launched in 2006. Its mission to study the interaction between magnetic field lines and the corona. Recently, it captured images of one of the waves thought responsible for heating this enigmatic region, Alfvén waves.
Alfvén waves are waves that occur in a plasma, in a bunch of ionized gas, threaded by a magnetic field. And indeed, it's thought that these Alfvén waves might be bringing turbulent energy from inside the sun out to the corona, where that energy heats the corona.
Energetic Alfvén waves form inside the sun and travel up through the surface, making the looping magnetic field lines sway and vibrate.
And so through this vibration or this oscillation, they're having friction with the magnetized plasma surrounding it in the corona. And through this friction, their heating occurs.
It's this heat delivered to the corona that radiates out into space, filling our solar system with the sun's energy. But this energy is not constant. Our sun is an ephemeral body, never the same from one day or 1 year to the next. Like Earth changes with seasons, so does the sun. And when the solar seasons change, anything can happen. Day in and day out, the sun we see appears the same. But like Earth, the sun has seasons, solar minimum and solar maximum. Two distinct personalities that can affect our technology and possibly even our weather. The transition between solar minimums is called the solar cycle, an average 11-year period in which the sun's activity maxes out, then ebbs again.
The primary measure of the solar activity cycle is the number of sunspots visible in the sun.
During solar minimum, the period with the fewest sunspots, solar activity is limited. When sunspots break through the surface during solar max, the sun's power reaches out.
When there are lots of sunspots, there are lots of flares and coronal mass ejections.
Increases in solar activity enhance the connection between sun and Earth. Energy expelled from the sun can create disturbances in the near-Earth environment.
The Earth is embedded in the solar atmosphere, and so what happens on the sun affects the Earth. And that's what we call space weather.
Accurate space weather forecasting is the ultimate goal, but this can be hard. The sun is turbulent, especially during solar maximum, the peak of solar storm activity.
During solar maximum, the magnetic field of the corona becomes very complicated, and you have magnetic field everywhere, all around, even near the poles. You can have coronal mass ejections and flares and solar storms occurring sometimes several times a day.
Solar flares, violent eruptions of energy, usually near sunspots, burst into space. Like a bolt of lightning, quick and powerful, they can happen over a matter of minutes and can give off the same amount of energy as 1 billion megatons of dynamite.
Solar flares are gigantic outbursts of energy from the sun, coming from a very small localized region of the sun's surface. So they're very concentrated ejections of energy that heat the surrounding gas to 10 million degrees.
Solar flare is sort of like a snapping of the whip. It really releases a lot of energy very quickly, accelerating particles almost up to the speed of light.
The particles from the very most energetic solar flares can reach us in something like 15 minutes.
But the solar hurricane of space weather comes from coronal mass ejections. These massive blasts carry billions of tons of superheated gas and plasma into interstellar space.
So coronal mass ejection is where a huge amount of mass and energy is expelled away from the solar surface. So if you can imagine this huge amount of mass and energy traveling away from the sun at these large speeds, sometimes at over 1 million miles an hour.
They throw these like big bubbles of hot gas and magnetic field. It can move off the sun so quickly that it actually creates a shock wave. They're the biggest storms, and they're the important ones for understanding space weather.
Solar probes, like SOHO, have captured the sun expelling massive amounts of energy into space. But scientists are most concerned when they see something called the halo effect, when the cloud of energy appears to surround the coronagraph. That means the sun has aimed its latest blast at us, like in the massive solar storms of 2003.
The fastest coronal mass ejection ever studied in modern times came from these storms.
Shortly after the initial blast from the sun, SOHO was bombarded by charged solar particles, protons and electrons, overwhelming the camera and causing the image to drop out.
What happens is you see a sort of snow on the camera, all sorts of sparkles going by, and that's the particles accelerated by the coronal mass ejection hitting the actual camera on SOHO.
If caught off guard, solar storms can harm astronauts, exposing them to the same amount of radiation in seconds that we receive on Earth in a year.
So if we're going to send astronauts back to the moon and to Mars, it becomes very important to be able to determine when these coronal mass ejections and storms are going to occur. The charged particles embedded in these coronal mass ejections are dangerous. It's a lot of radiation that would hit an astronaut.
Astronauts and satellites aren't the only potential victims of solar storms. The particles blasted towards Earth can interact with our magnetic field, occasionally wreaking havoc.
When this material comes smashing into the Earth's magnetic field, it causes it to ring almost like a bell. And when you have a magnetic field, and when that magnetic field moves, physics tells us it's going to create currents. And so electrical currents will be created in the outer atmosphere of the Earth. And these electrical currents can cause all sorts of disturbances.
The currents create problems for satellites orbiting the Earth. They disrupt global positioning systems. They can interfere with communications equipment, causing radio blackouts and knocking out mobile phone systems.
These mass ejections can send so many charged particles toward the Earth that some of them make it through the Earth's magnetic field and even reach power stations here on Earth, causing surges of electrons and power outages and short circuits and things like that.
In extreme situations, solar storms cause excessive radio interference and increased levels of radiation, requiring planes flying near the poles to be rerouted. But as powerful as the storms were in 2003, they're no match for what astronomer Richard Carrington saw in 1859, a superflare.
The super flare of 1859 was incredible because prior to this event, we didn't even know that flares existed. Carrington saw this huge bright flash on the sun with the unaided eye. And in order for him to see that, it had to have been a super huge flare.
There were reports of telegraph lines running without being powered.
We probably won't see another one that intense in our lifetime, although it's hard to say for sure. The sun has thrown us some surprises.
If a similar storm were to strike today, one recent estimate projects 130 million people would lose power, possibly for months.
Most of the electrical infrastructure, the power grids around the world, would be knocked out. A lot of the transformers would be overloaded. Having a large portion of the population with no power for many months could cost huge amounts of money. People have estimated that it would be upwards of $2 trillion.
We won't know unless it actually happens, and the more warning we get, the more we can do to reduce the economic impact, which is one of the reasons why we're studying the sun.
Scientists are a step closer to being able to predict these storms since the launch of the Solar Terrestrial Relations Observatory, also known as STEREO. This pair of probes now gives scientists the ability to see the sun in 3D.
So now, when one of these coronal mass ejections travels towards us, we're actually looking at the side view. And so we can see how fast they're traveling, we can see how they're evolving, the structure.
In 2011, the STEREO probes will reach their ideal vantage point, opposite sides of the sun, giving NASA a 360-degree view, allowing them to see what is coming from the far side of the sun before it impacts Earth.
And so for the first time, we're going to have a complete view of the sun all the way around. So this is going to allow us to see everything that's happening on the sun at the same time, and this will lead us again into a better ability to predict these types of storms.
But as dangerous as solar maximum can be for its increase in space weather, the sun's solar cycle counterpart and calmer period, solar minimum, may come with its own dangers.
When there are a low number of sunspots on the sun, the climate here on Earth can actually cool a little bit.
2008 saw the fewest number of sunspots in nearly a century, with a total of 266 sunspot-free days.
In 2008, we were at sunspot minimum, but by now we expected to be climbing out of that sunspot minimum, and we're not. So this could mean that this particular sunspot minimum is more protracted.
Scientists believe that past protracted minimums have had a chilling impact here on Earth.
Now, every once in a while, the sunspot activity cycle seems to just go away or become much diminished. There was such a period around 1650 to the early 1700s.
There were only about 50 sunspots recorded, when normally in the same time frame there are tens of thousands. So it was a really low period of sunspots.
It was called the Maunder minimum. The sun was in a quiet state. And that was associated with lower than normal temperatures here on Earth. Europe experienced sort of a mini ice age during those few decades.
Whether or not this current minimum will be protracted enough to have such a large impact on Earth won't be known for years. But another measure of solar activity, the solar wind, appears to be waning. And that could impact Earth tomorrow. Bathed in the sun's atmosphere, Earth is shielded from deadly cosmic rays. And while the sun's power protects us, it can also harm us. Life on Earth survives this close to its star, thanks in part to its ozone layer. But what would happen if the ozone layer were gone?
If Earth lost much of its ozone layer, ultraviolet radiation from the sun would penetrate through the atmosphere and reach the Earth's surface.
The sun's massive amounts of ultraviolet rays would quickly eliminate most basic elements of the food chain, wiping out plants and then animals.
If we are bathed in huge amounts of ultraviolet light, eventually the life on the Earth would die.
But what could cause such a catastrophic collapse of the ozone layer? Something the sun is supposed to protect us from: a gamma ray burst.
Gamma ray bursts are intense, brief flashes of the most energetic kind of radiation known, gamma rays.
The most powerful events in the universe. In seconds, they give off the same amount of energy that the sun will emit in its entire life. They occur when certain large mass stars die or even collide.
They can be generated from very extreme processes, such as large mass stars collapsing into black holes.
They occur somewhere in the sky roughly once per day, and they come from very, very far away. Most of them are billions of light years away.
But just 8,000 light years away, deep within the Sagittarius constellation, buried in a pinwheel-like formation, looms a potentially ticking time bomb. WR-104. Two stars locked in a cosmic dance, spinning a full rotation once every 8 months. But one of these stars is on the verge of going supernova and emitting a gamma ray burst.
Now, one of these two stars is a very massive star that might someday form a gamma ray burst, and its beam might hit the Earth. If the high-energy beam from a gamma ray burst were pointing directly at the Earth, it could spell real danger.
The radiation from the gamma ray burst would be so intense, very short, on the order of 10, 20 seconds, but this would set up a chain of events which eventually would deplete the Earth of maybe 50 or more % of the ozone layer.
Scientists have speculated that a nearby gamma ray burst caused an ancient extinction on Earth millions of years ago.
At the time, there was only sea life that existed. And even though the sea life deep beneath the sea wouldn't be directly affected by the UV radiation, the plankton and the life on near the surface would die off, and therefore the food chain would be affected.
The threat is heightened even further by something scientists have witnessed over the past few decades: a 20% decrease in the power of the sun's solar winds.
The solar wind is the steady emission of particles from the sun.
They carry the magnetic field that is in the solar corona out into space.
It exists even when there are no coronal mass ejections or solar flares.
The solar wind continues way out beyond the orbit of Pluto and has actually blown a bubble in interstellar space.
Now, that's a bit of a protective bubble because the magnetic fields protect us from charged particles coming from outside.
Normally, solar winds stream off the sun in all directions at speeds of 1 million miles per hour. Pulling the sun's invisible magnetic field along with it, they form the solar system's defense against intergalactic intrusion, the heliosphere.
The heliosphere is the very boundary where the solar wind hits intergalactic space. So it's this shell that's surrounding the sun and the solar system where it protects us from intergalactic winds here on Earth.
Recently, scientists have learned that the heliosphere is shrinking and getting weaker.
The solar wind pressure has been measured to be decreasing over the last 25 years. In fact, the heliosphere, where the solar wind pressure is extending out to, has actually shrunk a bit.
A weaker heliosphere increases the possibility that Earth will be exposed to harm from intergalactic cosmic materials.
So if there's less solar wind, then the heliosphere itself is going to shrink. That makes it easier for more cosmic rays to enter into the solar system.
Already, the amount of high-energy electrons, a small but telling aspect of cosmic rays around Earth, has jumped in number by 20%.
Looks like the cosmic ray electrons have increased, and you would expect that. If the solar wind has decreased by 20–30% over the last 15 years, the bubble will have gotten smaller, and you expect an increase in galactic cosmic rays.
The good thing for us is that we live on a planet with a thick atmosphere and a magnetic field. So we have two types of shields that protect us.
But that could change when WR104 emits its gamma-ray burst, possibly upsetting the balance of Sun and Earth, a balance that may already be in jeopardy because of something the Sun did billions of years ago. Over billions of years, the Sun and the Earth have developed the perfect balance for life to thrive. Sitting in the Goldilocks position of the solar system, not too hot and not too cold, the Sun gives us just enough light, just enough heat, and just enough energy to fuel our planet and our lives.
The Sun drives everything on the Earth. The Sun is the energy source of the Earth. So all of the energy that's given off by the Sun heats up the Earth. This drives weather. On a larger time scale, this drives climate. So basically the Sun is the energy source. It's the battery that drives the whole Earth environment.
Plants harness the Sun's energy through photosynthesis, creating carbohydrates. People and animals consume these carbohydrates, converting them into energy we can use. Even the fossil fuels that power our lives were created by the Sun. But our increased use of fossil fuels seems to be upsetting the balance between the Sun and the Earth.
Since all living material gets its energy initially from the sun is the source of the fossil fuels, whether it's trees, whether it's other things that have been trapped in the rock layer and then squeezed and slowly over millions of years made into the hydrocarbons that we know them as. And we then harvest and use those from underground.
The fossil fuels that we burn today unleash the Sun's energy from millions of years ago, overwhelming the balance struck between our planet and its nearest star.
If we burn all this, we will change the atmosphere unrecognizably long before we get to a point when we're actually running out of the resource itself.
Already, we have seen the effects of too much solar energy in the rise of global temperatures. The release of millions of tons of ancient solar energy stored in fossil fuels has amplified the necessary and natural process called the greenhouse effect.
Many people think that the greenhouse effect is a bad thing. Well, in fact, it's not. It keeps the Earth warm. Without the greenhouse effect, Earth's oceans would be frozen solid. What is bad is too much of a greenhouse effect. If there's too much carbon dioxide and water vapor and methane in the Earth's atmosphere, then those gases trap too much of the sun's radiation, elevating Earth's average temperature, leading to global warming. Now that can cause a melting of the polar caps and a rise in the ocean levels, leading to just a calamity on Earth if it happens too quickly.
Not only will our atmosphere continue to trap more heat, it could start to decay. Continued use of fossilized solar energy will allow in undesirable amounts of radiation from our sun. Right now, our ozone layer prevents the majority of the sun's ultraviolet radiation from reaching Earth, while allowing just enough sunlight to give us what we need to survive.
Sunlight interacting with our skin produces vitamin D, which is a very useful vitamin.
Vitamin D can protect us from a number of diseases, including the bone disorder osteoporosis and heart disease. But here, too, a balance has been struck. Too much sun can alter our DNA, causing skin cancer. Maintaining the equilibrium between sun and Earth that allows life to thrive will require using less of the sun's ancient energy and more of the energy it delivers on a daily basis. After all, the sun's energy output is estimated to be 386 billion megawatts. Meaning in 15 minutes, our star radiates as much energy as all life on Earth consumes in 1 year. Tapping this power source has been the goal of scientists for decades.
For sheer size, a solar satellite would be unprecedented. A structure 35 to 40 square miles covered with solar cells, able to capture the sun's energy 24 hours a day and beam it to Earth.
NASA has yet to achieve a goal on that scale, but their work with solar technologies in space has advanced technology here on Earth.
History of solar cells is essentially a technology that came back down to Earth from space. When we first started to work on the Apollo and Mercury and Gemini programs, we needed power plants in space. Solar cells were a natural way to do that.
Currently, we have two ways of directly harnessing the sun's energy. Solar thermal, which converts the sun's energy into heat by concentrating it enough to drive turbines, and solar panels, which use silicon-based technology to directly convert the energy from above into electricity. We can indirectly tap into the sun's power through wind turbines, capturing the energy produced by the weather the sun helps create. These technologies are constantly being improved. But some of the most interesting new science is coming from a very old process, photosynthesis.
There's some really exciting opportunities as we move from the world of semiconductor solar cells to organic ones.
Attempting to mimic Mother Nature, scientists have been able to create electricity from something found at the farmer's market, spinach.
There's organic molecules in spinach, in all green plants, but spinach happens to have a very convenient one, where you can harvest that peptide, that molecule.
Researchers were then able to put that peptide into a kind of solar sandwich, placing it between two electrically conductive materials.
And when it's exposed to sunlight, it will circulate electrons, which is current, which is electricity. So these organic molecules can actually become little solar cells.
In order to maintain the balance between Earth and our nearest star, it's become clear we must focus on finding ways to fuel our lives with the energy the sun supplies today. After all, the promise of solar energy is that for as long as the sun shines, its power can be ours. But what will happen when its power becomes too plentiful? The elements that make up the sun, the Earth, and even humankind all come from one place: stardust, the remains of stars that lived billions of years ago. And just as those stars died, so too will our sun.
In about 5 billion years, the sun will pretty rapidly become much more powerful, much brighter, and much bigger.
The sun will reach a stage where it has burned through all of its hydrogen. And once that happens, it will start to burn through all of its helium.
The sun will start to expand as it reaches a stage called a red giant. As it expands, it will start to expand into much larger size and fill the inner solar system.
The orbits of the planets themselves will actually expand outward as well, because it's not as massive.
During that stage, some instabilities, which I call cosmic burps, will cause the sun's outer atmosphere to be gently ejected.
The outer layers of the red giant will just keep drifting off at some slow rate.
The hot inner layers of the sun will ionize that cloud of gas surrounding it and cause it to glow. So our sun will be surrounded by these glowing clouds of gas.
They will form what's called a planetary nebulae. They're beautiful shapes. Some are just purely round, but some have been distorted into other shapes. They've come off non-symmetrically from the star underneath.
What'll remain is the contracting core of our sun, and it won't produce any new energy through nuclear reactions. because all the nuclear reactions will have stopped. So it'll continue contracting and slowly fading with time.
It's very similar to the process that creates, say, supernova, but our sun is not big enough, doesn't have enough stuff to actually create a supernova. So its final stage will be this object we call a white dwarf star.
What remains is this little, relatively small white dwarf star, and it is a very quiet, what we call happily retired star.
It'll be about the size of the Earth, it won't get any smaller, and it'll sit around as this very highly compressed rock forever. It'll just liberate its energy, growing ever colder and dimmer with time, until finally it just fades from view.
The death of the sun will have catastrophic effects on the solar system. If the massive expansion doesn't swallow the nearby planets, it will likely change their orbits and superheat them, including Earth.
Earth's surface will be fried to a crisp.
The Earth is probably going to get baked one way or the other.
I mean, imagine the sun being 100 or 200 times brighter than it is right now. Imagine how much the Earth would be heated. It would not be a pleasant place to be.
It actually may get baked before the sun completely dies, because the sun will get hotter even before it becomes a red giant and gets as large as the orbit of the Earth. It'll get warmer, and at some point the Earth will get hot enough so that water will boil.
So the oceans will evaporate away, and all of life as we know it will cease to exist.
If there's anything left of the Earth, the sun will shrink down to a white dwarf, and the Earth will, instead of heating, freeze.
This will not be a pleasant place to live.
But that's billions and billions of years from now. We've only had rockets in space, satellites, for 50 years or so. Now we're talking billions. So clearly we'll be able to travel around the solar system at the very least, to go to places that will be at the temperature that the Earth is now, and we'll be able, by that time, to go to more distant solar systems. So I don't spend a lot of time worrying about what's going to happen to the sun in 5 billion years.
The sun gave us our life, and it will eventually take it away. And though the Earth will die, it and everything on it will, in some part, live on. The stardust that gave...
Complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. A border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born like this from the death of a star, its diameter is 50 kilometers at most. But one can find black holes of truly monstrous proportions, over 10 billion kilometers in diameter. Andrea Ghez is an expert on this invisible phenomenon of the black hole. It was when she saw the Apollo moon landing on TV that her interest in space was awakened.
My biggest objective in life when I was very young was to become a ballerina. So I think I see things spinning in space now as opposed to myself. But yeah, your path the path was unclear. And today I view doing astronomy and studying the black hole as putting together one big puzzle.
Donald Lyndon Bell predicted that a supermassive black hole lurks at the heart of every galaxy. Andrea Ghez tried to find such a black hole in our own Milky Way galaxy.
Or actually, the first thing that we're trying to do is watch how stars move. That's the key to finding that there's a black hole. And the way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Ghez followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Ghez used one of the observatories on this summit, the Keck Observatory. The Keck has two of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Ghez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Galessen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours. So we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star which people were very excited about in the earliest days was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is 4 million times the mass of the Sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second. about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered this natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度に見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. a spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobayama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and congratulate you on your great discovery." The letter came from England. The sender? None other than Donald Lyndon Bell, who had predicted the existence of supermassive black holes.
I was very happy because I didn't feel that I absolutely knew. I thought it was likely, and I thought it was more and more likely.
A black hole equivalent to 39 million solar masses was sucking in huge volumes of gas with its tremendous gravitational force. The dark object in the center of this artist's conception is a black hole. Its diameter is awesome, as if 160 of our suns were lined up in a row. It is now thought that almost all galaxies have these supermassive black holes at their center. The most advanced observational instruments are detecting ever larger black holes. Situated outside Earth's atmosphere, the Hubble Space Telescope can see space objects with great clarity. Hubble took aim at NGC 7052, a galaxy located 37 million light-years away. The image it captured was that of a huge disk, comprised of gases and stars. In its center, there ought to be a supermassive black hole.
When we got this image, I was just super excited, because it was such beautiful, rich detail that I really knew right when I saw this that we were going to be able to get, excellent spectra and really be able to determine whether this galaxy has a black hole and how massive it is. So I was very, very excited.
The galaxy was indeed harboring a supermassive black hole. A black hole equivalent to 300 million solar masses. That's more than 70 times larger than the one at the center of our own Milky Way galaxy. A black hole with the diameter of 1,200 of our suns lined up in a row. And Hubble has spotted an even larger one, an ultramassive black hole. This one is in M87, 59 million light-years away. Scientists had long been puzzled by a band of white light there. When Hubble was trained on the galaxy's core, the band of white light was revealed to be a gigantic jet of gases. As the gases are sucked violently into the black hole, a portion of them are ejected in the form of this jet. The mass of the black hole at the base of this jet has been calculated to be 6.4 billion solar masses. That's 10 million times greater than the supermassive black hole at the center of our Milky Way galaxy. In size, its diameter is equal to 25,000 of our suns lined up in a row. Then, in 2011, the largest black hole in history was discovered. In the galactic nucleus of NGC 4889, there's an unimaginably monstrous black hole, with a mass equivalent to 9.7 billion times that of our Sun. What scientists are most eager to elucidate now is the process by which these black holes become so large. They may start with the death of a star, but how do they then grow to billions of times their original size? Trinity College at the University of Cambridge. Isaac Newton, who formulated the universal law of gravitation, conducted research here. Martin Rees has served as Master of Trinity College. Rees has conducted research on supermassive black holes together with Lyndon Bell. The impetus for his research was the discovery of galaxies whose high-energy cores were emitting powerful radio waves.
Well, there were various alternative theories about what might be happening in the centers of the galaxies, which are putting out a concentrated high source of power. And these ideas included a very dense cluster of stars, a very massive star, a binary supermassive object, etc. And I realized that if you followed forward the likely evolution of any of these objects, they would all have no alternative to becoming a big black hole.
So any object emitting sufficiently high amounts of energy will inevitably become a supermassive black hole. How then are supermassive black holes born? The Rees diagram, as it was called, charted the possible routes.
If you're going to be at that, you need to have...
In the 30 years since the Rees diagram was published, there has been a succession of discoveries of supermassive black holes. At the same time, the study of their birth has also been progressing. One scenario suggested by Rees was the consolidation of several smaller black holes. At the end of their lives, stars explode, forming relatively small black holes. Hundreds of millions of them may cluster together, merging into one supermassive black hole. This is NASA's space-based Chandra X-ray Observatory. Chandra has been examining a region where black hole consolidation is thought to be taking place. Galaxy NGC 6240 is located 400 million light-years from Earth. Actually, two galaxies are colliding there. As Chandra examines their galactic cores, two bluish-white spots appear. They are both massive black holes, one at the center of each galaxy.
This blue region here is a blow-up of the center, and you can see there are two little sources there, one brighter and one a bit fainter. But each of those, when we look at the spectrum, shows a very characteristic sign that this is just emission from a supermassive black hole in each case, which has never been seen before until we had the beautiful Chandra image and could separate the two.
Two black holes in close proximity to each other, but they cannot soon merge. Rather like the Earth and the Moon in their perpetual dance, the two black holes orbit about each other without colliding. So what about Rees's concept of black holes merging to form a supermassive black hole? Masayuki Umemura uses a supercomputer to create simulations of black hole mergers. Here, he simulates the behaviors of 10 black holes of equivalent mass. The first consolidation happens far sooner than expected. It takes only 50 million years. The process repeats. Within about 500 million years, 5 black holes have merged into one.
もともと銀河が持っていたブラックホールが、大きな銀河に取り込まれたときにブラックホールごと、中に取り込まれるわけですね。そうすると2つではなくて、例えば大きな銀河の中に10個のブラックホールがあるというような状況が最初に起こった可能性が高いということをまず想定しました。
Let's look at our actual universe. There are galactic collisions and mergers all over the place. And when galaxies merge, the thinking is that their black holes merge too. Wherever galaxies cluster, there's bound to be a cluster of black holes. That means a process of consolidation of black holes. This conforms to actual observations of our universe. A second Rees diagram scenario has a seed black hole becoming supermassive by swallowing up gases and stars. In that scenario, the monster is born by gulping down an unbelievable quantity of gases, equivalent to hundreds of millions of our sun. The gases are sucked in with so much force that the friction produces incredible heat. That violent process emits intense light and X radiation and blows away surrounding gases. The result is that there are no more gases to feed on, and the black hole ceases to grow. But how is it that such a huge quantity of gases could be sucked in the first place? Gases that are being sucked in, blowing away other gases. Ken Osuga studies this contradiction. He has found a particular mechanism within black holes by which they can continue to draw in vast amounts of gases. He's prepared a simulation of one scenario for how supermassive black holes may be created. As a black hole sucks in gases, it generates magnetic field lines, which penetrate the surrounding gas disk like hoops. Thus embedded, they are then distorted by the swirl of the disk. As the disk swirls, the The magnetic field lines are caught in a spiral vortex, twisted and coiled like a spring. This is a plasma jet. A portion of the disk's gases, charged with energy such as light, shoots out in opposite directions perpendicular to the disk. Any remaining gases are sucked into the black hole, which grows supermassive.
私たちの研究の結果はですね、光の力が非常に強くなったとしても、ジェットは噴出するけども、ガス円盤からガスは変わらず吸い込まれ続けるということを明らかにしました。これによってですね、ブラックホールは大量のガスを吸い込むことができますので、巨大ブラックホールに成長するのに一役買うということを証明することができました。
Hubble has captured this actual image of an intense jet erupting from the center of a galaxy. The gas-guzzling scenario for supermassive black hole creation, as outlined in the Rees diagram, thus seems persuasive. Martin Rees developed several theories of supermassive black hole formation. One was by the continuing consumption of gases. Another was by the consolidation of smaller black holes. But the Rees diagram indicated a third possibility as well. Under this third scenario, just after the creation of the universe, large clouds of gas condensed into supermassive black holes directly, without first becoming stars at all. Recently, evidence for this third scenario has also come to light. By combining information from the Chandra X-ray and Hubble Space Telescopes, Priya Natarajan hunts for supermassive black holes created at the inception of the universe. These far-off galaxies were photographed by Hubble. Among those circled on the screen are some that are 12 billion light-years away. They are small galaxies, born immediately after the universe itself. Some 200 of them have been identified. Here's one as perceived by Chandra. And it already has a supermassive black hole in it. Natarajan was surprised to discover that almost all 200 of them had supermassive black holes in them. If so many supermassive black holes were already present immediately after the creation of the universe, then that lends powerful support to the third scenario in the Rees diagram.
So just as we think that a gas cloud that is collapsing could make the first star reasonably easily, the conditions that you need for making a black hole seed directly without forming a star, instead of forming a star, also exist in the early universe.
Efforts are also underway to confirm the third Rees diagram scenario computationally.
I think it is the first time that there is a model showing that it is possible to produce a precursor of a big black hole in the form of this supermassive black hole.
This is a giant gas cloud, 100 light-years in diameter. 70,000 years after it formed into a gas cloud, its gases were compressed into a disk 1 light-year across. The gas disk was equivalent in mass to 100,000 of our suns. It then condensed further, compressed by its own weight, giving rise to a supermassive black hole. So the third scenario in the Rees diagram, going directly from gas cloud to black hole, is a real possibility. Studies of the origins of these supermassive black holes are ongoing. The latest research reveals that the supermassive black holes do not simply grow fat, consuming everything nearby. Surprisingly, they exert a huge constructive effect on the space around them. What these remarkable monsters call home is a galaxy's core. More specifically, it's inside the concentration of stars called the bulge. The shape and size of the bulge varies with each galaxy. John Cormandy has investigated the relationship between the mass of a bulge and of its supermassive black hole. The first galaxy he observed was Andromeda. The supermassive black hole here is equivalent to 150 million solar masses. The bulge is approximately 1,000 times greater in mass. Next, he looked at the Sombrero Galaxy. The black hole here is 1 billion solar masses. The mass of the bulge is approximately 1,000 times that. Plotted on a graph coordinating the masses of the bulges with those of the black holes, the galaxies form a nearly straight line. In most galaxies, the black hole to bulge ratio of masses is 1 to 1,000. This strong relationship between the mass of supermassive black holes and their galaxies' bulges surprised many scientists.
We know that when gas densities get very big, you get a burst of new stars being formed. And so at the same time when this burst of stars is making the bulge, the rest of the gas is being fed to the black hole and making the black hole bigger. So you get lots of new stars and you get higher mass black hole, and the two correlate.
A galaxy comprises hundreds of billions of stars. It turns out that at the galactic cores, the black holes and the bulges have a deep interrelationship. A giant bulge will correlate with a giant black hole. A small bulge with a small black hole. This strange law of outer space may mean that galaxies and black holes evolved together. Andrea Ghez discovered the supermassive black hole at the center of our own Milky Way galaxy. She also found evidence that it performs an astonishing function within the galaxy's bulge.
We've had one surprise after another in our study of the center of the galaxy. What we see is that they're very massive stars, which tells us that they're very young stars. And the last thing you expect near a black hole is to find a very young star, because black holes are very inhospitable to star formation. They should just tear apart any cloud that might eventually become a star. So you really don't expect to see young stars, baby stars near a black hole. And yet all the stars that told us that there's a black hole are the ones we predicted shouldn't be there. So it's one mystery after another.
Near the supermassive black hole at the center of the Milky Way, Gez found many baby stars. This suggests something astounding, that new stars may be emerging from the gases that originally accumulate around a black hole. The effect black holes have on surrounding space is not limited to the birthing of stars. A project spearheaded by NASA called Tanami is endeavoring to capture distant galaxies. Tanami involves the participation of radio telescopes in a dozen locations in the southern hemisphere, chiefly in Australia, but also in Chile, South Africa, and the South Pole. One of its targets is a galaxy located 14 million light-years from Earth, Centaurus A. This is the image they obtained, a clear view of a plasma jet violently shooting out from an invisible black hole. The jet bursts out at 30% of the speed of light. Analysis of this jet turned up something quite unexpected. The jet shooting out of the black hole even escapes the galaxy itself. Its plume expands for a distance of 1 million light-years. So the black hole doesn't just guzzle down gases, it sends out the stuff that stars are made of far beyond its own galaxy. The role of the supermassive black holes in the universe is still largely mysterious, but scientists are learning more and more.
Cosmos looks the same from Britain and from Japan. Indeed, the night sky is the same to all of us and has been the same to all our ancestors throughout human history. It's the one common feature of all humanity. They've all looked up at the night sky and wondered at it and interpreted it in their own way. It's a wonderful story where we found all these extraordinary objects in the universe and we can understand these vast cosmic horizons in a way that our ancestors could only have dreamed of. So it's a wonderful story.
Supermassive black holes, monsters in the galactic cores. They may gobble up everything around them, but they also give birth to stars and send out energy-rich materials into the universe. Some came into being at the same time as their galaxies and grew along with them. He was interested in a galaxy adjacent to the Big Dipper. Galaxy M106, a spiral galaxy 21 million light-years from Earth. Radio waves had been reported to be issuing regularly from the nucleus of M106.
銀河の中でそういう規則正しく電波、光もそうですけど、変わるというのはそういう現象はほとんどないんです。だから非常に驚いてですね、本当にそういう、電波の強さが規則正しく変わっているのかどうかというのを調べようとしたんです。
In addition to a 45-meter diameter parabolic dish antenna, the Nobeyama Radio Observatory has some world-class instrumentation. 8 spectrometers capable of minute observation of radio waves. A single spectrometer is sufficient to observe radio waves from the nucleus of a galaxy. But to be thorough, Nakai used 2 spectrometers for the very center of the galaxy and flanked them with the 6 remaining ones. That decision to use all 8 instruments led to the discovery of the century. Nakai had simply wanted to put all his spectrometers to some use, but the results astonished him. There were surprising spikes on both ends of the combined graphs. Nakai was especially struck by the ones on the left. This indicated something moving at high velocities never before observed.
今まで銀河でですね、そういう大きな速度に見つかったことは全くないわけです。これに気がついた時にはもう体中がですね、熱くなりましてですね、これはとんでもないことだというふうに思いましたけど。
More detailed observations were made using a high-resolution telescope. They found something remarkable at the core of the galaxy. A spinning disk. This was a structure very like the disk formed by gases being sucked into a black hole. The spikes recorded by the 8 Nobeyama spectrometers were from this disk. The disk was spinning furiously, 3.6 million kilometers an hour. Detailed analysis revealed that the mass at its center was equivalent to 39 million of our suns. It was indeed a monster black hole.
45メーターなければそういうブラックホールは見つかってなかったです。それから電波分光計が8台なければですね、とても見つかってなかったですね。
When his discovery was published in 1995, Nakai received a letter. The letter read, "I have been waiting 26 years for such proof, and
4 million times the mass of the sun.
Finally, after 10 years of observations, it was determined that a supermassive black hole does in fact exist in the center of our galaxy. And it is bigger than was imagined, by many orders of magnitude. Black holes created when stars die are typically 50 kilometers in diameter at most, but the one at the center of our galaxy is gigantic. The diameter is estimated to be 24 million kilometers. That's like 17 of our suns lined up in a row. Round this monster black hole rushes SO2, a giant blue star, at 5,000 kilometers per second, about 200 times the speed at which the Earth orbits the Sun. That is a speed made possible only by the immense gravitational pull of a black hole. In the center of our own galaxy, but far from Earth, unfolds a dance of the stars. It was this dancing of the stars that proved the existence of a supermassive black hole.
It was an idea, but, you know, far out and not very much considered this natural, and it remained that way for about 15 years.
Lyndon Bell had predicted that a supermassive black hole exists at the center of every galaxy. Apart from observing the orbits of the stars, there's another way to prove the existence of such a black hole. That's to observe the moment when a black hole swallows up stars or gases. As gases are sucked into a black hole, they first flatten into a disk. Friction causes them to superheat, and to emit intense radio waves. If these radio waves can be detected, that can indicate the presence of a black hole. The largest telescope in the world for detecting extremely high-frequency millimeter-band radio waves is the 45-meter radio telescope at the National Astronomical Observatory of Japan. It was in fact a Japanese scientist who first proved Lyndon Bell's theory that a supermassive black hole lies hidden in every galaxy. It happened in 1990, 21 years after Lyndon Bell's prediction. Naomasa Nakai was working at the Nobeyama Radio Observatory, studying gases at the centers of galaxies. Shine much more clearly. Gez, who did not yet have adaptive optics, was at a disadvantage. She minimized atmospheric fluctuations by restricting exposure time in imaging the stars. Meticulously, she charted their movements. Success or failure depended on choosing the right stars to follow. At first, both teams were following a star designated SO1. But Gez's attention was drawn to another star.
Another star which people were very excited about in the earliest days was SO1. It was the star that was moving fastest initially. But it was SO2 that, as it got closer to the black hole, has become the fastest moving star that we've known about.
This graphic represents Gez's findings. Knowing that stars orbit the center of the galaxy was not enough to prove the existence of a black hole. In January of 2002, another star, designated SO2, was observed to be behaving strangely. It was executing a blindingly fast and tight orbit, clocked at 5,000 kilometers per second, as if being swung violently around and around.
These were incredibly exciting times because, of course, at every stage of this experiment, people said, you can't do it, or what you're seeing isn't what you should be seeing. So we initially saw that they were moving fast, and people said, well, these stars aren't bound to the galaxy. You're not going to see them curve.
Yet SO2 was indeed curving in a rapid orbit. This is an actual imaging sequence. Exhaustive analysis showed it to be a giant star with a mass equivalent to 10 suns.
The only thing that can make stars move that fast is a lot of mass. These stars are moving because there's a lot of gravity. And the only thing that makes that much gravity in that small a space is a supermassive black hole.
With their adaptive optics, the strange behavior of SO2 had not escaped the notice of the European team either. They succeeded in imaging SO2 at around the same time.
Of course, that was the moment everybody was extremely excited about, that we saw, wow, that orbit is proving there must be a mass, and we can measure the mass, we can actually calculate the mass. It's an easy calculation, any student can do it, and the result is extremely fascinating. This mass, which we are seeing in these images, is...
The way you do this is by pointing your telescope at the center of the galaxy and using a technique that allows you to see the stars around the black hole. So here's the black hole. And what you want to do is we want to be able to see a star. You want to be able to see a star make a complete orbit around the center.
Gez followed the movements of the stars for years, plotting their trajectories. If they were in fact orbiting some unseen object, then that would be proof of a black hole. The center of the Milky Way, however, is 26,000 light years from Earth. Ascertaining the movements of stars around a point so far off in space is no easy matter. Mauna Kea, Hawaii, home to several giant telescopes. Gez used one of the observatories on this summit, the Keck Observatory. The Keck has two of the largest telescopes in the world, with primary mirrors that are 10 meters in diameter. Gez's observations here began in 1995. But Gez and her team were not the only ones searching for a supermassive black hole in the center of our galaxy. A European team based in the heart of Germany had also been hunting the same monster. The leader of these star trackers is Stefan Galessen.
They have a 10-meter telescope. We have an 8-meter telescope. So our telescope is a bit smaller. However, we are on the southern hemisphere, where the galactic center is visible for more hours. So we can observe from February to October.
The European team conducts its observations at the Paranal Observatory in Chile. The VLT array there comprises 4 8.2-meter telescopes. But even with such advanced technology, success is elusive. The problem is Earth's atmosphere. Atmospheric fluctuations blur the stars. April 2002, the European team installs epoch-making new equipment. From the VLT at Paranal, they shoot laser beams into the night sky to measure and adjust for those atmospheric fluctuations. Their special equipment succeeds in doing just that. The new method is called adaptive optics. It brings the stars into focus. Corrected for atmospheric fluctuations, the stars shine. The black hole is a bizarre space object, defined by the absence of everything except gravitational force. How do scientists wrap their minds around it? It's complicated. Seriously massive objects warp the fabric of space. The heavier the star, that is, the greater its mass, the greater the distortion. So light, which would otherwise travel in a straight path, gets bent. If a star of any given mass shrinks sufficiently, its density increases until its local distortion of space is infinite. That's a black hole. border develops separating the black hole from the space around it. Once this border has been crossed, going into the black hole, even light cannot escape. Border diameter is determined by the weight of the compressed mass. A hole with the same mass as Earth would be merely 2 centimeters across, something the mass of the Sun, 6 kilometers. That's considered the size of the black hole. Black holes are created the instant stars die. Let's say a star 20 or more times larger than our Sun reaches the end of its life and explodes. The star's own gravity then causes its remaining core to implode infinitely, becoming a purely gravitational force. When a black hole is born,
from the drama of our planet's origins and the birth of our solar system comes one of the most startling revelations of modern science. The solar system we see today, quiet, stable, was once a battlefield. Newborn planets blasted through space, competing for stable, circularized orbits inside a grunge-style mosh pit of gas and dust. For those that find the right balance, the prize is survival. For the rest, world-shattering destruction. A new look at the chaos of creation and a frightening possibility in our distant future. Mars. The Curiosity rover is searching for clues about the origins of the red planet. It confirms the presence of oxygen and nitrogen isotopes hidden in the rocks and soil.
We use isotopes to try to figure out the history of planets, partly because they are immune to many of the changes, the chemical changes that occur when you have things like collisions and so forth. Isotopes, the relative abundances of these isotopes are like fingerprints.
Curiosity confirms a unique mix of isotope fingerprints. The isotopes indicate that Mars formed elsewhere in the solar system and moved into our neighborhood. Our solar system is full of oddities pointing to an imperfect birth and a malformed evolution. All of our planets go around the Sun in the same direction that the Sun is spinning. This is the same direction that the clouds within our original nebula began to rotate. 6 planets spin around their poles in the same direction. For them, the Sun rises in the east and sets in the west. Yet 2 planets spin the opposite direction. For Venus and Uranus, the Sun rises in the west and sets in the east. Uranus not only has a retrograde spin, it rolls on its side like a bowling ball. At Neptune, the icy moon Triton orbits backwards, opposite from the direction of Neptune's spin. Do these planets spin backwards because they were rocked by titanic collisions in the past?
So we see evidence in the architecture of the solar system for not only collisions like Earth's moon and the fact that Venus is rotating in the wrong direction and Uranus is on its side and so forth. All these things are attributed to collisions. We also see in the asteroid belt and in the Kuiper belt, the outer asteroid belt if you like, we see that the orbits of these things look like they've been disturbed.
closer to home, our own Earth has an inexplicable 23.5-degree tilt. Its spin axis is radically misaligned from its magnetic pole. And our moon is comparatively large for a planet our size. Now, a new theory may be able to explain many of these oddities. It is called the Grand Tack hypothesis. Four and a half to 5 billion years ago, a gas giant planet arose inside a primordial disk of gas and dust.
Jupiter didn't just form where it is, but formed and then moved inward towards the sun.
As it spirals toward the sun, Jupiter herds asteroids and rubble.
Jupiter's natural tendency is to drift in slowly through this debris field that it's traveling around.
The inner solar system is also thick with gas and dust. The planetary system is well underway. Numerous worlds are born in this region, including the Earth. Primordial skies are ruled by chaos. Jupiter's approach destabilizes these planets. Their orbits decay into wildly swinging ellipses. Some are tossed out. Others fall into the sun. Their numbers are unknowable. These are ghost worlds from a bygone age.
Jupiter just causes all heck to break out in the solar system, and all that debris in the outer solar system gets flung inward towards the inner solar system.
And it was a busy time in the very early solar system, and things were colliding with each other all the time.
And then it stopped. Jupiter's invasion of the inner solar system is mysteriously halted. The planet makes a turn, or, in sailors' parlance, a grand tack. Lurking behind Jupiter is a second gas giant, Saturn.
So as Jupiter was migrating inward, Saturn was following it and growing. And as Saturn was growing, it came to have a size that it had a gravitational impact on Jupiter, which became more important than the gravitational interaction between the gaseous disk and Jupiter. They reverse direction. And in a sense, you can think of Saturn and Jupiter feeding off one another and moving back out.
Gravity tugs each passing planet.
Is exert a very subtle little periodic force at the right time, and you can have amazing changes in the motion of the object you're pushing on.
Once enough energy has been transferred, the planets synchronize their orbits. They are said to be in a resonance. For planets, resonances are achieved and maintained through the mutual push and pull of gravity through the fabric of space. They're a key factor in the continuing evolution of our solar system. This effect can be duplicated in the lab.
We have 10 metronomes here set up on a swinging platform. They have little weights on pendulums here, but they've all been set at the same frequency. And I'm going to try to start them as best I can, completely out of phase, randomly. So their oscillation is going to transfer energy by the swinging of this plastic sheet to the other metronomes that are out of phase to get into phase with the majority. It's inevitable that there's going